Hello there, and welcome to Science for Sleep, where curiosity slows down, questions unfold gently, and the universe becomes a quiet place to wander just before rest. Tonight, we're going to explore something vast, mysterious, and strangely hidden, even though it influences the motion of entire galaxies. It has a name that sounds almost mythical, like something whispered about in old star charts or half-forgotten observatory notes. Astronomers call it the Great Attractor. Now, that name alone can feel a little dramatic, so let's soften it for a moment and think of it in a calmer way. Imagine standing beside a slow, wide river at dusk. You cannot see the far bend where the water disappears beyond the trees, but you can sense the current pulling steadily in that direction. Leaves drift past you, small twigs follow, and somewhere far upstream, whole branches move with the same quiet certainty. You don't need to see the bend to know something lies that way, shaping the flow. In a way, the Great Attractor is like that unseen bend in the river of galaxies. It's not something we can easily look at, not something shining brightly in telescopes like a nearby star or a colourful nebula. Instead, it reveals itself through motion, through the slow drifting of enormous structures across unimaginable distances. Entire clusters of galaxies, including our own cosmic neighbourhood, are moving in a particular direction, as though carried by a current far larger than anything we normally picture when we think about space. Before we drift any farther into that idea, I'd like to ask you something simple. Where are you listening from tonight? Maybe you're at home, the lights low, the quiet hum of a distant street outside. Maybe you're listening through headphones, tucked into bed, or sitting somewhere peaceful where the world has finally slowed down. And what time is it for you right now? Late evening, perhaps, or early morning in another part of the world. It's always a little comforting to remember that while each of us experiences a different hour, we can still share the same story, the same gentle journey of thought. If you find this kind of slow exploration soothing, or if you simply enjoy letting your mind wander through science at an unhurried pace, I'd be grateful if you gave the video a like or subscribe to the channel. It helps this quiet little space reach others who might need a calm moment at the end of their day. And now, with that said, let's settle in and begin our journey. To understand the Great Attractor, it helps to start with a simple question. How does anything move in space at all? We often picture the universe as static, like a painted ceiling of stars, but in reality everything is in motion. The Earth spins, the Earth orbits the Sun moves through the Milky Way, and the Milky Way itself drifts among other galaxies in a vast cosmic landscape that is anything but still. For a long time, astronomers assumed that on the larger scales these motions were fairly straightforward. Galaxies recede from one another as the universe expands, like dots on the surface of a balloon as it inflates. This expansion was discovered in the early 20th century, and it became one of the central ideas of modern cosmology. Space itself stretches, carrying galaxies along with it. But then, as measurements became more precise, scientists began to notice something curious. Galaxies weren't just drifting apart in neat, predictable ways. Many of them seemed to have additional motions, small deviations like boats on an outgoing tide that also feel local currents and eddies. These deviations are called peculiar velocities, and they can tell us something about the gravitational influences acting on galaxies. Gravity, after all, doesn't stop working just because distances are large. Every bit of matter pulls on every other bit of matter, and when enormous amounts of mass gather in one region of space, the effect can be felt across hundreds of millions of light years. Astronomers began mapping these peculiar motions, comparing how fast galaxies should be moving due to cosmic expansion with how fast they were actually moving, and what they found suggested something unexpected. Large groups of galaxies spread across an immense region of space were all drifting in roughly the same direction. Not randomly, not in scattered patterns, but with a shared motion, as though something far away was exerting a steady gravitational pull. At first, This was puzzling. The sky in that direction didn't appear especially remarkable. There were no obvious giant clusters blazing with light, no clear sign of a massive structure capable of influencing so much matter. Yet the motion was there, measurable and persistent. Imagine noticing that every leaf floating on a pond slowly drifts toward one shadowy corner, even though you cannot see what lies beneath the surface there. You might suspect a submerged rock, or a gentle inflow of water, something hidden but powerful enough to shape the movement of everything around it. That is essentially what astronomers realized in the late 20th century. Something enormous seemed to lie in a particular region of the sky, pulling galaxies toward it. And because its nature was uncertain, and because its presence was inferred rather than directly seen, it was given a name that captured both its influence and its mystery: the Great Attractor. One of the reasons this object remained hidden for so long has to do with our own position in the Milky Way. We live inside a spiral galaxy filled with stars, gas, and dust. When we look outward into the universe, that material can block our view, especially in certain directions. There is a broad band of sky where distant galaxies are obscured by the dense disk of our own galaxy. Astronomers sometimes call this region the zone of avoidance, not because there is nothing there, but because it is difficult to observe. The Great Attractor happens to lie in that general direction, behind thick curtains of interstellar dust and crowded star fields. Observing galaxies beyond it is like trying to study a distant city through a dense forest at night. You may catch glimpses of light, hints of structure, but the full picture remains elusive. Over time, astronomers developed new techniques to peer through this cosmic fog. Radio waves, infrared observations, and careful measurements of galaxy motions began to reveal more detail. What emerged was not a single object, not a solitary giant pulling everything inward, but a complex region of immense mass, including clusters of galaxies and vast amounts of matter, much of it visible. And that invisibility brings us to another important idea, one that quietly underlies much of modern astronomy. Most of the matter in the universe does not shine. It doesn't emit light, it doesn't reflect light, and it doesn't interact strongly with ordinary matter except through gravity. This is what scientists call dark matter, and it outweighs the familiar atoms of stars and planets by a wide margin. So when we speak of something as massive as the Great Attractor, we're not only talking about visible galaxies, we're also talking about enormous halos of dark matter, structures that can outweigh the luminous parts many times over, shaping the motion of galaxies like invisible scaffolding. If you pause for a moment and picture that, it can feel strangely calming rather than unsettling. The universe is not just the bright points we see in the night sky. It is also vast, silent structures that do their work quietly, shaping the path of galaxies over billions of years, without hurry, without noise. Our own galaxy, the Milky Way, is part of this motion. Along with our neighbouring galaxies, we're drifting through space at hundreds of kilometres per second, carried by gravitational influences that extend far beyond anything we can see with the naked eye. It is a gentle journey on human timescales, far too slow to notice in a lifetime, but steady and real nonetheless. Sometimes it helps to bring these enormous ideas down to something more familiar. Think of standing in a large crowd at a train station. At first, people move randomly, some walking quickly, others slowly, some stopping to check their phones. But then, somewhere in the distance, a platform opens, and gradually the crowd begins to drift in that direction. No one person causes the motion, and many people may not even be aware of the reason at first, yet the flow becomes clear if you step back and watch. Galaxies behave in a somewhat similar way. Individually, they have their own motions, their own local interactions, but on the larger scales, patterns emerge, flows that reveal the presence of massive structures shaping the universe. The Great Attractor is part of one of those patterns, a signpost pointing towards something immense. And yet, the more astronomers study it, the more they realise that it may not be a single destination at all, but part of an even larger structure, a vast region of interconnected galaxy clusters and dark matter stretching across hundreds of millions of light years. We'll take our time with that idea later, because understanding the true scale of these structures requires a bit of patience and a willingness to let the mind expand gradually, the way your eyes adjust to darkness. For now, it's enough to sit with the thought that our galaxy is not standing still. It is moving, slowly but surely, through a cosmic landscape shaped by gravity on scales that are almost beyond imagination. And perhaps there is something comforting in that motion. The Earth turns, the seasons change, tides rise and fall, and even galaxies drift along currents set in motion long before our sun was born. Movement, it seems, is part of everything, from the smallest atoms to the largest clusters of galaxies. In the quiet of the night, when the world feels still, it can be soothing to remember that stillness is often just motion too slow to notice, change unfolding at a pace far gentler than our daily lives. What makes the Great Attractor so fascinating is that, for a long time, no one could actually see it. Not in the ordinary sense, anyway. There was no brilliant cluster dominating the sky, no obvious beacons shining through telescopes, nothing that would immediately make astronomers point and say, "There it is." Instead, the first clues appeared in a much quieter way, hidden in numbers, in measurements, and in the patient work of mapping how galaxies move. To understand how this discovery unfolded, it helps to picture what astronomers were doing in the middle of the 20th century. By then, they already knew that the universe was expanding. Galaxies, on average, move away from each other as space itself stretches. The farther away a galaxy is, the faster it recedes, a relationship known as Hubble's law. This idea gave scientists a kind of baseline expectation. If you know how far away a galaxy is, you can estimate how fast it should be moving due to expansion alone. But galaxies are not just carried along by the expansion of the universe. Gravity still plays its role. Nearby galaxies tug on each other. Clusters of galaxies pull on surrounding matter. These additional motions, layered on top of expansion, are what astronomers call peculiar velocities. The name sounds a bit whimsical, but it simply means motion that differs from what the expansion of space would predict. During the 1960s and 1970s, astronomers began measuring these velocities with increasing precision. They studied clusters of galaxies and tried to map how they were moving relative to one another. At first, the results looked messy, a scatter of motions in many directions, but as more data accumulated, patterns began to emerge. One of the most intriguing patterns involved our own cosmic neighbourhood. The Milky Way is part of a small group of galaxies known as the Local Group, which in turn belongs to a larger structure called the Virgo supercluster. For a while, astronomers assumed that the gravitational pull of the Virgo cluster, a massive collection of galaxies about 50 million light-years away, explained most of our motion through space. Yet when scientists measured the motion of galaxies more carefully, something didn't quite add up. The direction and speed of our galaxy's movement suggested that Virgo alone could not account for it. The pull seemed stronger, and it seemed to come from a region farther away. This realization did not arrive all at once. It came gradually through the work of several research groups comparing observations, refining methods, and sometimes questioning their own results. Science often advances in this way, not with sudden flashes of certainty, but with slow adjustments, like turning the focus ring on a telescope until the image becomes just a little clearer. By the late 1970s and early 1980s, the evidence was becoming difficult to ignore. Large numbers of galaxies spread across enormous distances appeared to be drifting in roughly the same direction. The motion was not random. It was coherent, as though these galaxies were being drawn toward a common centre of gravity. The difficulty was that this apparent centre lay in a part of the sky that was notoriously hard to observe. The dense disk of the Milky Way blocks our view in certain directions, filling telescopes with the light of countless stars and the obscuring haze of interstellar dust. Behind that barrier, distant galaxies become faint or invisible, not because they are absent, but because their light cannot easily reach us. This region became known informally as the zone of avoidance. It sounds almost mysterious, but the name simply reflects the practical challenge astronomers faced. When mapping the large-scale distribution of galaxies, there was a broad band across the sky where data was sparse, not because the universe was empty there, but because our own galaxy was in the way. And it was precisely in that direction that the mysterious pull seemed to lead. Imagine trying to map a distant landscape while a mountain stands directly in front of you. You might see rivers flowing toward the far side of the mountain, forests thinning in that direction, clouds gathering above some unseen valley. Even without seeing the valley itself, you could infer that something significant lies there, shaping the terrain. Astronomers found themselves in a similar position. They could not see the source directly, but the motion of galaxies pointed toward it unmistakably. In 1986, a team of researchers studying galaxy velocities in the Centaurus and Hydra clusters identified a region that seemed to contain an enormous concentration of mass. They estimated that this region lay roughly 150 to 250 million light-years away in the direction of the Centaurus constellation. It appeared to be pulling galaxies toward it, including our own. Because the object was inferred rather than directly observed, and because its true nature was uncertain, it was given a name that captured both its influence and its mystery: the Great Attractor. The name quickly caught the imagination, not only among scientists but also among the public. It sounded almost like something from a science fiction story, a hidden giant lurking behind the stars. In reality, the Great Attractor is not a single object like a star or even a single galaxy cluster. It is a region of space containing multiple clusters, enormous quantities of dark matter, and structures so vast that they challenge ordinary ways of thinking about size. One of the key structures associated with the Great Attractor is the Norma cluster, also known as Arbel 3627. This cluster is extraordinarily massive and lies near the centre of the region believed to dominate the gravitational pull. When astronomers finally managed to observe it more clearly using X-ray and infrared telescopes, they realised it was one of the richest galaxy clusters in the nearby universe. Clusters like Norma are not small gatherings. Each one can contain hundreds, or even thousands of galaxies, along with vast reservoirs of hot gas and immense halos of dark matter. The total mass of such a cluster can be measured in quadrillions of times the mass of the Sun. And yet, even a cluster that massive may not fully account for the observed motion of galaxies. The Great Attractor appears to be part of something larger still, a network of clusters and superclusters forming a kind of gravitational basin on a scale that is difficult to visualize. At this point, it can be helpful to pause and consider how astronomers measure something so distant and so elusive. After all, galaxies are not labelled with neat tags indicating their speed and direction. These measurements require careful observation of light, particularly the way light shifts as objects move. When a galaxy moves away from us, its light is stretched to longer wavelengths, becoming slightly redder. This effect, known as redshift, allows astronomers to estimate how fast the galaxy is receding. By comparing redshift with independent measurements of distance, scientists can determine whether a galaxy is moving faster or slower than expected from cosmic expansion alone. It is a bit like watching boats on a river. If you know how fast the current is flowing, you can tell whether a boat is drifting with the current, rowing against it, or being pulled sideways by some hidden eddy. Over decades, astronomers compiled enormous catalogues of galaxy redshifts and distances. Patterns emerged, revealing streams of galaxies moving together, like schools of fish in a vast ocean. These streams converged towards certain regions, one of which lay behind the zone of avoidance. The realization that galaxies form such large-scale flows was itself a profound discovery. It showed that the universe is not random on the larger scales, but structured, with filaments, clusters, and superclusters forming a kind of cosmic web. Gravity shapes this web over billions of years, pulling matter into denser regions and leaving vast voids in between. The Great Attractor sits within this web, not as a solitary monster, but as part of a larger landscape of mass and motion. Another intriguing piece of evidence for our motion toward this region comes from the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This radiation is remarkably uniform, but it shows a slight temperature difference depending on the direction we look. One side of the sky appears a tiny bit warmer, the opposite side a tiny bit cooler. This pattern, called the dipole anisotropy, indicates that our galaxy is moving relative to this background radiation at about 600 kilometers per second. That motion must have a cause, and the gravitational pull of massive structures, including the Great Attractor and even more distant concentrations of matter, helps explain it. If you think about that speed for a moment, it sounds enormous, and by everyday standards it certainly is. Yet on cosmic scales, it is a gentle drift, a steady migration taking hundreds of millions of years to cover distances between clusters. What is perhaps most remarkable is how long it took to uncover this story. The Great Attractor was not discovered with a single telescope or a single observation. It emerged from the combined work of many scientists, using different instruments, different wavelengths of light, and different methods of analysis. Piece by piece, the evidence accumulated until a coherent picture began to form, and even now, that picture is still being refined. New surveys, more powerful telescopes, and improved computer simulations continue to reveal details about the large-scale structure of the universe. The Great Attractor is no longer seen as an isolated curiosity, but as part of an even larger flow of galaxies extending toward regions like the Shapley supercluster, an immense concentration of mass hundreds of millions of light-years farther away. So the discovery of the Great Attractor was not just the identification of a hidden object. It was a step toward understanding how matter is distributed on the larger scales, how gravity shapes the motion of galaxies, and how our own Milky Way fits into a vast, interconnected cosmic landscape. There is something quietly humbling in that realization. For most of human history, the night sky appeared fixed and unchanging, a dome of stars turning slowly overhead. Now we know that everything is in motion, drifting through space along paths shaped by forces acting across unimaginable distances. And yet, despite these immense movements, the night still feels calm when we step outside and look up. The stars shine steadily, the air is still, and the sense of quiet remains. The motion of galaxies is too slow to see, too gradual to feel, unfolding over timescales far longer than a human life. It becomes natural to ask how astronomers can map such enormous structures in the first place. How do you chart something hundreds of millions of light years across, especially when much of it is hidden behind our own galaxy? Long before anyone spoke about a Great Attractor, long before maps of superclusters and cosmic flows filled the pages of astronomy journals, there was simply a quiet sense of unease in the data. Not the kind of unease that suggests a mistake or a broken instrument, but the gentler kind that appears when measurements are consistent, repeatable, and yet not quite what theory predicts. Astronomers were measuring how galaxies moved, and what they were finding hinted that something large and unseen was influencing the motion of our entire region of space. To understand how that realization emerged, it helps to return for a moment to a simpler picture of the universe, the one that guided astronomers through much of the 20th century. After Edwin Hubble's discovery that galaxies are receding from one another, the expanding universe became a foundational idea. Galaxies are carried apart as space itself stretches, and the farther away a galaxy is, the faster it moves away from us. This relationship was not just a theory, but something that could be measured directly by observing the redshift of galaxies. In that picture, motion seemed straightforward. Expansion provided the main pattern, like raisins drifting apart in a rising loaf of bread. If that were the whole story, then once you accounted for expansion, galaxies would appear mostly at rest relative to the general flow. There might be small local motions caused by nearby neighbours, but nothing too dramatic on very large scales. Yet when astronomers began measuring galaxy distances and velocities with greater precision, they noticed something intriguing. Some galaxies were moving slightly faster or slower than expected. Others seemed to drift sideways relative to the expansion. These deviations were small compared with the overall expansion, but they were real, and they were systematic enough to attract attention. These additional motions became known as peculiar velocities. The term sounds almost humorous, but it carries a precise meaning. A peculiar velocity is simply the velocity of a galaxy relative to the smooth expansion of the universe. It represents the influence of gravity from nearby and distant matter. At first, peculiar velocities were not surprising. Gravity had always been part of the cosmic story. Galaxies within clusters orbit one another, and clusters themselves interact gravitationally. But as measurements improved, astronomers began to see patterns that extended far beyond individual clusters. In the 1970s, surveys of galaxies in our local region of the universe began to reveal something subtle but persistent. Galaxies within tens of millions of light-years of the Milky Way appeared to share a common drift. It was as if our entire neighbourhood was moving together, not randomly but in a coordinated way. Imagine standing in a wide, shallow lake watching leaves float on the surface. At first, each leaf seems to move independently, nudged by tiny ripples or breezes. But after a while, you notice that many leaves are drifting slowly in the same direction. The movement is gentle, almost imperceptible, but unmistakably shared. That is the kind of pattern astronomers began to detect. The first hints came from studies of nearby galaxy clusters such as Virgo and Hydra. These clusters showed motions that could not be explained solely by the gravitational pull of visible matter within them. Something larger seemed to be shaping the motion of entire regions of space. One important clue came from observing the Milky Way itself. Our galaxy is not stationary. It moves relative to the cosmic microwave background, the faint glow left over from the Big Bang. This motion can be measured with remarkable precision by examining tiny temperature differences in that background radiation. When scientists analysed these measurements, they found that the Milky Way is moving at roughly 600 kilometers per second relative to the cosmic microwave background. That speed is astonishingly high by everyday standards, yet it is also remarkably smooth and consistent. It suggests that our galaxy is not being jostled randomly, but is drifting along a gravitational gradient, pulled toward regions of greater mass. The direction of this motion became a subject of intense study. By comparing the movement of many galaxies, astronomers could trace the overall flow of matter. The results pointed toward a region of the sky in the general direction of the Centaurus and Norma clusters. At first, researchers suspected that the Virgo cluster, relatively nearby in cosmic terms, might account for much of this motion. Virgo is massive, containing thousands of galaxies and enormous quantities of dark matter. Its gravitational pull certainly affects the Milky Way and other galaxies in the local group. But calculations showed that Virgo alone could not explain the observed velocities. The numbers simply did not match. The pull was too strong and the direction slightly off. Something farther away, something more massive had to be contributing. This realization did not arrive as a single dramatic announcement. It emerged gradually, through careful comparisons of data sets, improvements in distance measurements, and the patient work of astronomers cross-checking each other's results. Science often moves this way, not in sudden leaps, but in slow, steady refinements that eventually reveal a clear pattern. By the early 1980s, the evidence for large-scale flows of galaxies had become compelling. Entire clusters were moving together toward a common region of space. The motion extended across distances of hundreds of millions of light-years, far larger than any single cluster or supercluster known at the time. And yet, when astronomers looked in that direction, they encountered a frustrating obstacle. The region lay behind the dense plain of the Milky Way, where dust and stars obscure distant objects. It was like trying to study a distant mountain range while standing in the middle of a forest. You could sense its presence from the way rivers flowed and clouds gathered, but seeing it directly was difficult. This hidden region began to take on an almost mythical quality. Researchers could measure its gravitational influence, but its true nature remained elusive. The galaxies in our region of the universe seemed to be falling towards something they could not fully observe. One of the key breakthroughs in understanding these motions came from the development of better methods for measuring galaxy distances. Determining how far away a galaxy is may sound straightforward, but in practice it is one of the most challenging tasks in astronomy. Astronomers use a series of techniques known as the cosmic distance ladder. For nearby stars, they measure parallax, the tiny shift in position caused by Earth's orbit around the Sun. For more distant objects, they rely on standard candles, objects with known intrinsic brightness, such as certain types of variable stars and supernova. By comparing intrinsic brightness with observed brightness, they can estimate distance. Once distances became more accurate, astronomers could compare them with redshift measurements to calculate peculiar velocities more precisely. The patterns that emerged were striking. Galaxies were not simply expanding away from each other, they were streaming along vast gravitational currents. These flows became known as bulk motions, and they revealed that gravity shapes the universe on scales far larger than previously imagined. Instead of isolated clusters drifting randomly, entire regions of space were moving coherently, drawn toward massive concentrations of matter. At this point, it is helpful to pause and consider the scale of what was being observed. A single galaxy contains hundreds of billions of stars. A cluster may contain thousands of galaxies. A supercluster spans hundreds of millions of light years. And yet, astronomers were seeing motions that extended across distances larger still. It was as though continents on a cosmic ocean were drifting slowly toward a distant shore. Another important line of evidence came from studies of galaxy distributions. When astronomers mapped the positions of galaxies across large areas of the sky, they discovered that matter in the universe is not evenly spread. Instead, it forms a vast web of filaments, clusters, and voids. Galaxies tend to gather along these filaments, leaving enormous empty regions in between. This cosmic web provides a natural pathway for large-scale flows. Matter moves along filaments toward denser regions, much as water flows through rivers toward the sea. The strange motion of galaxies was not random at all. It was part of a larger pattern, one that reflected the underlying structure of the universe. As researchers traced these flows, they found that many of them converged toward a region that would later be called the Great Attractor. The name was not meant to imply a single object, but rather a gravitational centre toward which galaxies were drifting. The realization that our own galaxy was part of this flow was both exciting and humbling. The Milky Way, which had once seemed like a vast and dominant structure, turned out to be just one participant in a much larger movement. There is something quietly comforting in that thought. We often imagine ourselves as stationary observers, watching the universe from a fixed point. But in reality, we are travellers, carried along by motions that began billions of years ago. And yet, despite these immense movements, nothing feels hurried. The drift of galaxies is so slow that it unfolds over timescales far beyond human perception. Even travelling at hundreds of kilometres per second, a galaxy would take millions of years to move a noticeable distance relative to its neighbours. So the strange motion of galaxies, once puzzling, gradually became a clue, a signpost pointing toward hidden structures and unseen mass. It showed astronomers that the universe is not just expanding but also flowing, shaped by gravity on the largest imaginable scales. As observations improved, the picture grew clearer. The Great Attractor was not a single mysterious object but part of a vast region of mass, including clusters like Norma and extending toward even larger concentrations such as the Shapley supercluster. The flow of galaxies turned out to be part of an enormous gravitational landscape, one that continues to be mapped in ever greater detail. How do you chart something so vast that light takes hundreds of millions of years to cross it? How do you trace structures that are partly hidden behind our own galaxy? One of the quiet challenges in astronomy is that motion in space is not something you can watch directly, at least not in the way you might watch clouds drift or leaves fall. The distances are simply too vast and the timescales too long. A galaxy may move hundreds of kilometers every second, yet over the span of a human lifetime, that motion is so small compared with its distance from us that it appears perfectly still. So when astronomers began to realize that entire regions of galaxies were drifting together, the question naturally followed: how can you measure motion that unfolds over millions or billions of years? The answer, like many things in science, lies in patience, careful observation, and a willingness to rely on indirect clues. Astronomers do not see galaxies moving across the sky in real time. Instead, they measure properties of light, compare distances, and build maps that reveal patterns invisible to the eye alone. To begin with, it helps to think about how distance itself is measured in astronomy, because motion only makes sense once distance is known. If you see a car on a road, you can estimate how fast it is moving partly because you know how far away it is. Without that sense of scale, speed becomes difficult to judge. The same principle applies in space. Astronomers have developed a series of techniques known collectively as the cosmic distance ladder. Each step of this ladder works over a certain range, and together they allow distances to be measured across the observable universe. For nearby stars, the most direct method is parallax, which relies on the Earth's motion around the Sun. As the Earth orbits, nearby stars appear to shift slightly against the background of more distant stars. By measuring that tiny shift and applying a bit of geometry, astronomers can calculate the distance. Parallax works beautifully for stars within a few thousand light-years, especially now that space telescopes can measure incredibly small angles. But galaxies lie far beyond that range, so astronomers must rely on other methods. One of the most important tools is the use of standard candles. These are objects whose intrinsic brightness is known. Certain types of stars, such as Cepheid variables, pulsate in a way that reveals how luminous they truly are. By comparing how bright they appear from Earth with how bright they actually are, astronomers can calculate their distance. It is rather like seeing a familiar lamp across a field at night. If you know how bright the lamp is, you can estimate how far away it must be based on how dim it looks. Farther still, astronomers use exploding stars known as Type 1a supernovae. These events reach nearly the same peak brightness wherever they occur, making them reliable markers across enormous distances. By observing such supernovae in distant galaxies, scientists can extend their distance measurements hundreds of millions or even billions of light-years outward. Once distances are known, the next step is to measure how fast galaxies are moving. This is done through the study of redshift, one of the most important tools in cosmology. Light behaves as a wave, and when the source of that light moves away from us, the wavelength stretches, shifting toward the red end of the spectrum. The amount of this shift reveals how fast the object is receding. For galaxies, this redshift is usually dominated by the expansion of the universe. The farther away a galaxy is, the faster it appears to be moving away, simply because space itself is expanding. But when astronomers subtract this expected expansion, they sometimes find that a galaxy is moving a little faster, or a little slower than predicted, or even drifting sideways relative to the general flow. That additional motion is the peculiar velocity, the key to mapping gravitational influences. If enough galaxies in a region share similar peculiar velocities, it suggests they are responding to the same gravitational pull. This is how astronomers began to detect large-scale flows of galaxies long before they could clearly see the structures responsible. Another technique involves studying the distribution of galaxies themselves. By mapping the positions of thousands or millions of galaxies, astronomers can trace the large-scale structure of the universe. These maps reveal filaments, clusters, and vast empty voids, forming what is often called the cosmic web. Matter tends to flow along these filaments toward denser regions, much as streams merge into rivers. Creating such maps requires enormous surveys. Telescopes scan large areas of the sky, recording the positions and redshifts of galaxies one by one. Over time, these observations build up into three-dimensional maps, showing not only where galaxies are located, but how they are moving relative to one another. One of the challenges in mapping the Great Attractor region, as mentioned earlier, is that much of it lies behind the dense disk of the Milky Way. Dust and gas in our galaxy absorb visible light, making distant galaxies difficult to detect. But astronomers are resourceful, and light comes in many forms beyond what our eyes can see. Infrared observations can penetrate dust more effectively than visible light, revealing galaxies otherwise hidden. Radio telescopes can detect emissions from neutral hydrogen gas, allowing astronomers to identify galaxies even when they are obscured optically. X-ray telescopes can observe the hot gas that fills galaxy clusters, often glowing brightly at high energies even when individual galaxies are hard to distinguish. By combining observations across different wavelengths, astronomers can gradually fill in the gaps, building a more complete picture of regions once thought inaccessible. It is a bit like exploring a landscape in fog by using not only sight but also sound, touch, and careful measurement of the ground beneath your feet. There is also a remarkable method known as the Tully-Fisher relation, which allows distances to spiral galaxies to be estimated based on their rotation speed. Spiral galaxies spin, and the faster they spin, the more luminous they tend to be. By measuring the width of spectral lines from a galaxy, astronomers can determine how fast it is rotating, estimate its true brightness, and therefore calculate its distance. This method has been especially useful in studying galaxy flows because it provides distances independent of redshift. By comparing the redshift-derived velocity with the distance-derived expectation, astronomers can determine peculiar velocities and trace the motion of galaxies relative to the expanding universe. Over time, thousands of such measurements were gathered, revealing patterns that could not be explained by local gravitational effects alone. Galaxies across vast regions were moving in similar directions, as though following gentle slopes in a gravitational landscape. To visualize this, some researchers began creating maps not just of galaxy positions, but of galaxy velocities, representing motion as arrows or streams. These maps showed large-scale flows converging towards certain regions, including the area associated with the Great Attractor. Another important tool in understanding these motions comes from studying the cosmic microwave background. This faint radiation fills all of space and provides a kind of universal reference frame. Because it is so uniform, any motion of our galaxy relative to this background produces a measurable effect, a slight temperature difference across the sky. This effect, known as the dipole anisotropy, allows astronomers to determine both the speed and direction of our motion through space. When combined with galaxy surveys, it provides strong evidence that the Milky Way and its neighbouring galaxies are part of a large-scale flow toward massive structures. As computers became more powerful, astronomers began running simulations of cosmic structure formation. These simulations start with the conditions of the early universe and allow gravity to shape matter over billions of years. The resulting virtual universes show filaments, clusters, and flows strikingly similar to what we observe. They also help scientists estimate how much unseen mass, dark matter, must be present to produce the observed motions. Dark matter plays a central role in these maps. Although it cannot be seen directly, its gravitational effects are measurable. Galaxies rotate faster than visible matter alone can explain. Clusters hold together more strongly than expected, and large-scale flows require enormous amounts of mass. By including dark matter in their models, astronomers can account for these observations and better understand the forces shaping galaxy motions. Mapping the unseen is not a single process, but a combination of many methods. each providing a piece of the puzzle: distance measurements, redshift surveys, infrared and radio observations, cosmic microwave background studies, and computer simulations all contribute to a gradually improving picture. There is something quietly satisfying about this kind of work. It is not dramatic or hurried. It unfolds over decades, sometimes generations, as new instruments are built and new data collected. Each observation adds a small detail, like a brushstroke in a vast painting. And yet, the result is extraordinary. From a small planet orbiting an ordinary star in the outskirts of one galaxy, we have learned to trace the motion of structures hundreds of millions of light-years away. We have learned that galaxies do not drift randomly, but follow patterns shaped by gravity on scales that once seemed unimaginable. It is also worth remembering that these maps are not static. The universe continues to evolve, and our understanding continues to grow. New surveys, such as those conducted with next-generation telescopes, are revealing even larger structures and more subtle flows, extending our maps farther into the depths of space. As these maps become more detailed, the Great Attractor itself appears less like a single mysterious object and more like a region within a vast network of mass, connected to other massive concentrations such as the Shapley supercluster. The motion of galaxies, once puzzling, now appears as part of a grander pattern, a slow and steady movement through a cosmic landscape shaped over billions of years. If you pause for a moment and imagine that landscape, it may help to think of valleys and hills, not of earth and stone, but of gravity itself. Galaxies drift along gentle slopes, drawn toward regions of greater mass, their paths guided by forces acting across immense distances. The motion is unhurried, almost serene, unfolding over timescales so long that even the rise and fall of civilizations would pass unnoticed within a single step of the journey. What kind of structure could exert such influence across so vast a region of space? Is the Great Attractor a single cluster, a chain of clusters, or part of something even larger still? One of the more curious facts about the Great Attractor is that its mystery does not come from distance alone. Astronomers routinely observe galaxies billions of light-years away, detecting faint signals that have travelled across most of the age of the universe. In many cases, looking far away is easier than looking in certain nearby directions. The difficulty with the Great Attractor is not that it is unimaginably distant, but that something much closer stands in the way. That obstacle is our own galaxy. When we look up at the night sky from Earth, the Milky Way appears as a faint cloudy band stretching from horizon to horizon under dark conditions. To the unaided eye, it looks delicate, almost transparent, like a thin veil of light. But in reality, that band represents a dense, crowded disk containing hundreds of billions of stars, along with vast clouds of gas and dust. From our position embedded within it, looking outward through the plane of the Milky Way is a bit like trying to study distant mountains while standing inside a thick forest at night. The trees are close, numerous, and bright, and they obscure much of what lies beyond. Astronomers have a name for the region of sky, where this obscuration becomes especially severe. They call it the zone of avoidance. The name might sound dramatic, but it is simply a practical description. In maps of galaxy distributions, this zone appears as a broad band where few galaxies are recorded, not because they are absent, but because they are hidden behind the dust and stars of our own galaxy. The dust is particularly important. Interstellar dust consists of tiny particles of carbon, silicates, and other materials, often smaller than grains of smoke. These particles are extremely effective at absorbing and scattering visible light. When light from distant galaxies passes through dense clouds of dust, much of it never reaches our telescopes. The galaxies are still there, but they fade into the background, swallowed by the glare and haze of the Milky Way. For early astronomers working with optical telescopes, this presented a serious limitation. Large-scale surveys of galaxies, especially in the mid-20th century, showed a conspicuous gap along the plane of the Milky Way. It was as though a wide stripe had been erased from the cosmic map, and it was precisely in that stripe that the strange motions of galaxies seemed to be pointing. At first, this created a kind of observational puzzle. Measurements of galaxy velocities suggested that something massive lay in that direction, exerting a gravitational pull across enormous distances. Yet when astronomers tried to observe that region directly, they saw very little beyond the crowded foreground of our own galaxy. It was rather like feeling a strong breeze coming through a closed door without being able to see the landscape on the other side. To understand why the Milky Way blocks our view so effectively, it helps to picture the structure of our galaxy. The Milky Way is a spiral galaxy, shaped somewhat like a flattened disk with a central bulge. Most of its stars, gas and dust lie within this disk, which is only a few thousand light-years thick but more than 100,000 light-year across. Our solar system sits within this disk, about halfway from the centre to the outer edge. Because we are inside the disk, looking outward along its plane means looking through tens of thousands of light-years of stars and dust. The density of material increases dramatically compared with looking out of the plane, where the view opens into the relatively clear expanse above or below the galaxy. This difference is easy to notice even with the naked eye. When you look toward the Milky Way band, the sky is filled with stars. When you look far from it, the sky becomes darker and emptier, revealing distant galaxies that would otherwise be hidden. For astronomers trying to map the universe, this uneven visibility creates a challenge. Large-scale galaxy surveys must account for the missing region, using statistical methods and observations at other wavelengths to fill in the gaps. The development of radio astronomy in the 20th century provided one of the first ways to peer through the zone of avoidance. Radio waves have much longer wavelengths than visible light, and are far less affected by dust. Neutral hydrogen gas, which is abundant in galaxies, emits radiation at a specific radio wavelength known as the 21 centimeter line. By detecting this emission, astronomers can identify galaxies even when they are completely invisible in optical images. Using radio telescopes, researchers began to detect galaxies hidden behind the Milky Way, gradually revealing structures that had been concealed for decades. It was like discovering a city behind a thick fog by listening for the distant hum of traffic. Infrared astronomy provided another powerful tool, infrared light, which lies just beyond the red end of the visible spectrum, can penetrate dust far more effectively than visible light. Space telescopes designed to observe in infrared wavelengths began to uncover galaxies and clusters in regions once thought nearly empty. As these techniques improved, astronomers started to see that the zone of avoidance was not empty at all. It contained galaxy clusters, filaments, and large-scale structures much like the rest of the universe. Among these hidden structures was the region associated with the Great Attractor, including the massive Norma cluster. The Norma cluster turned out to be one of the richest clusters of galaxies in the nearby universe, comparable in mass and size to well-known clusters that had been studied for decades. Yet for a long time, it remained largely unnoticed simply because it lay behind the dense plane of the Milky Way. X-ray observations added another layer of understanding. Galaxy clusters are filled with extremely hot gas, heated to millions of degrees, which emit strongly in X-rays. Space-based X-ray telescopes can detect this emission even when optical observations are difficult. By mapping X-ray sources in the direction of the zone of avoidance, astronomers identified additional clusters and confirmed the presence of large concentrations of mass. Each of these methods, radio, infrared, and X-ray, acted like a different kind of vision, allowing astronomers to see through the dust in ways that earlier generations could not. Piece by piece, the hidden landscape began to emerge. Still, mapping this region remains more difficult than mapping clearer parts of the sky. Observations must be carefully corrected for the effects of dust extinction, and distinguishing distant galaxies from foreground stars can be challenging. The Milky Way contains so many stars that even high-resolution images can resemble a crowded field, where faint galaxies are easily overlooked. Another complication arises from the way dust absorbs different wavelengths unevenly. Some colours of light are absorbed more strongly than others, altering the apparent brightness and colour of objects seen through dusty regions. Astronomers must account for these effects when estimating distances and intrinsic properties of galaxies. Despite these challenges, progress has been steady. Surveys combining multiple wavelengths have revealed that the region behind the Milky Way is rich in structure, with clusters and filaments extending across vast distances. The Great Attractor itself is now understood to be part of a larger network of mass concentrations that shape the motion of galaxies over hundreds of millions of light-years. There is something quietly reassuring about the way this knowledge has unfolded. The universe did not hide the Great Attractor out of malice or mystery. It was simply a matter of perspective. From our position within the Milky Way, certain directions are harder to see. Given time, patience, and new technology, those hidden regions gradually come into view. It is a reminder that limitations in observation do not necessarily mean limitations in reality. Often, what seems invisible is simply waiting for a better way of looking. If you imagine the process of mapping the hidden universe, it might help to think of assembling a puzzle in dim light. At first, many pieces seem missing, and the picture appears incomplete. But as the light improves and more pieces are found, the image becomes clearer. The gaps shrink, patterns emerge, and what once seemed mysterious begins to make sense. Even now, the zone of avoidance is not fully mapped. New instruments and surveys continue to reveal additional galaxies and structures, refining our understanding of the mass distribution in that region. Each new observation helps astronomers better estimate the gravitational forces acting on our galaxy and others nearby. A few decades ago, if you had asked an astronomer where our galaxy belonged on the larger scales, the answer would probably have been simple and familiar. The Milky Way, they would say, is part of the local group, which is part of the Virgo supercluster. That description worked well enough for a long time. It gave a sense of structure, a hierarchy of galaxies within clusters, clusters within larger groupings. It felt orderly, like describing a town within a county within a country. But as observations improved and galaxy surveys expanded, that picture began to feel incomplete. The Virgo supercluster, once thought to be a clearly defined structure, turned out to be only a portion of something much larger, something whose boundaries were not defined by where galaxies were located, but by how they moved. This shift in perspective was subtle but important. Instead of asking only where galaxies are, astronomers began asking where galaxies are going. Motion, it turned out, could reveal structures that position alone could not. To understand this idea, it helps to imagine standing in a landscape shaped by hills and valleys, but covered in fog so thick that you cannot see the terrain itself. If you watch carefully, though, you might notice streams of water flowing across the ground. Even without seeing the hills, you could trace the slopes by following the paths of the streams. Water flows downhill, and by mapping its movement, you can reconstruct the shape of the land. Galaxies behave in a similar way. They drift along gravitational gradients, moving toward regions of greater mass. By mapping these motions, astronomers can identify gravitational basins, enormous regions of space where matter flows inward toward a common center. In 2014, a team of researchers used this approach to redefine our cosmic neighborhood. By analyzing the motions of thousands of galaxies, they identified a vast region within which galaxies share a common flow, all drifting toward the same general gravitational center. They named this region Laniakea. The name comes from the Hawaiian language and means immense heaven, or spacious sky, a fitting description for something that spans hundreds of millions of light years. Laniakea is not a cluster or even a single supercluster in the traditional sense. It is a gravitational basin, a region defined by the flow of galaxies rather than by sharp physical boundaries. Our galaxy, the Milky Way, lies within this basin. To picture the scale of Laniakea, it helps to begin with smaller structures and work outward. The local group, which includes the Milky Way, the Andromeda Galaxy, and dozens of smaller galaxies spans about 10 million light-years. The Virgo cluster, the nearest large cluster of galaxies, lies about 50 million light-years away. These distances are already vast beyond ordinary comprehension, but Laniakea extends across roughly 500 million light-years and contains the mass of about 100,000 large galaxies, along with immense quantities of dark matter and hot gas. It is so large that light, travelling at its incomprehensible speed, would take hundreds of millions of years to cross it, and yet even this immense structure is not defined by a solid boundary. Instead, its edges are determined by where the flow of galaxies changes direction. Galaxies within Laniakea drift toward one region, while galaxies just beyond its boundary drift toward different gravitational centres. The borders are more like watersheds on a continent than walls or edges. At the heart of this basin lies the region associated with the Great Attractor. It acts as one of the major centres of gravity drawing galaxies inward, though it is not the only influence. Beyond it lies an even larger concentration of mass known as the Shapley supercluster, whose gravitational pull extends across enormous distances. What makes the concept of Laniakea so illuminating is that it shows how interconnected these structures are. Instead of isolated clusters scattered randomly, the universe on large scales resembles a network of basins and flows, a cosmic landscape shaped by gravity over billions of years. The way astronomers mapped Laniakea is a story in itself, one that illustrates how motion can reveal hidden patterns. Researchers collected data on galaxy velocities, measuring how fast galaxies were moving relative to the cosmic expansion. By subtracting the expansion component, they could determine peculiar velocities, the motions caused by gravitational influences. Then they used computer models to trace these motions backward and forward, identifying regions where flows converged. The result was a map showing streams of galaxies flowing along filaments and into gravitational basins, much like rivers flowing into lakes and seas. When this map was visualized in 3 dimensions, the structure of Laniakea became apparent. It was not a neat sphere or a tidy cluster, but a sprawling, irregular region shaped by the distribution of matter and the slow pull of gravity. There is something quietly humbling about realizing that our galaxy is part of such a vast flow. For most of human history, the Milky Way was the entire universe, as far as anyone knew. Later it became one galaxy among billions, and now even our local supercluster is understood to be only a small part of a much larger gravitational landscape. Yet this realization is not unsettling. In a way, it can feel calming. We are not isolated in a dark and empty void, but part of a structure, part of a pattern that extends across unimaginable distances. The same laws of gravity that cause an apple to fall, or the moon to orbit the Earth, also guide the motion of galaxies across hundreds of millions of light-years. The idea of a gravitational basin also changes how we think about motion in the universe. It is not that galaxies are rushing toward a single point in some dramatic cosmic collision. The motions are gentle, measured in hundreds of kilometers per second, unfolding over billions of years. At that pace, even travelling for the entire history of human civilization, our galaxy would barely have moved a fraction of the distance to the Great Attractor. Another interesting aspect of Laniakea is how it fits into the larger cosmic web. Beyond its boundaries lie other superclusters and basins, each with its own patterns of motion. The universe on the larger scales resembles a network of filaments and nodes, with matter flowing along the filaments toward denser regions. These filaments themselves are separated by enormous voids, regions where few galaxies exist. Some voids span hundreds of millions of light-years, making them among the largest structures in the universe. The contrast between dense filaments and empty voids gives the cosmic web its distinctive appearance in simulations and surveys. When you see images of these structures, often rendered in glowing colours and delicate lines, it can be tempting to think of them as static, but they are not. They are evolving, slowly changing over billions of years as gravity pulls matter into denser regions, and the expansion of the universe stretches space itself. In this sense, Laniakea is not just a structure but a process, a snapshot of a gravitational flow that has been unfolding for much of cosmic history. It is also worth remembering that our understanding of these enormous structures is still incomplete. Observations continue to improve, and new surveys are revealing details that were once invisible. The boundaries of Laniakea may be refined, and our understanding of the Great Attractor's role within it may evolve. Science often works this way. Each new discovery adds depth to the picture, sometimes confirming earlier ideas, sometimes reshaping them. The map of the universe is not a finished document, but an ongoing project, drawn and redrawn as our view becomes clearer. If you pause for a moment and imagine our place within Laniakea, it can be helpful to picture standing on the deck of a slow-moving ship at sea. The water appears calm, the horizon distant and unchanging, yet the ship is steadily drifting with the current. You do not feel the motion directly, but it is there, carrying you across vast distances over time. Our galaxy is much like that ship, carried along by the gentle currents of gravity, part of a basin so large that it takes hundreds of millions of years for light to cross it. The Great Attractor lies somewhere ahead in that flow, not as a destination we will ever reach, but as a region shaping the motion of everything around it. When we speak of something so large, how do we even begin to grasp its scale? What does it really mean for a structure to span hundreds of millions of light years, and how can we place that scale in terms that the human mind can begin to hold? Trying to understand the size of something like a supercluster is a little like trying to understand the size of an ocean while standing on the shore. You can see the water stretching out, you can hear the waves, you can even sail across part of it, but the full scale never quite fits inside your mind all at once. The numbers involved become so large that they begin to feel abstract, almost detached from ordinary experience. And yet, with a bit of patience, it is possible to build up a sense of scale step by step, starting from things that feel familiar and gradually expanding outward. To begin, it helps to remember that the Earth itself once felt unimaginably large. For most of human history, travelling a few hundred kilometres was a journey of weeks or months. Entire cultures lived and died without ever seeing lands beyond the horizon. Today, we can cross continents in hours, and the Earth feels smaller than it once did, not because it has changed, but because our perspective has changed. Astronomy works in much the same way. The universe has not grown larger since we first began studying it, but our ability to measure and comprehend its scale has expanded dramatically. Each new step outward requires a new way of thinking, a new comparison, a new mental anchor to hold on to. Let's begin close to home, with distances that, while still enormous, can at least be related to something familiar. The Moon is about 384,000 kilometres from Earth. That distance is large enough that light, travelling at the fastest speed possible in the universe, takes a little over a second to make the journey. Sunlight takes about 8 minutes to reach Earth. Even within our solar system, distances quickly grow vast. Neptune, the outermost major planet, orbits about 4.5 billion kilometres from the Sun, and sunlight takes more than 4 hours to reach it. Already, we are far beyond anything encountered in everyday life. But the solar system is only a tiny neighbourhood within the Milky Way galaxy. Our galaxy spans roughly 100,000 light-years from one side to the other. A light-year, of course, is the distance light travels in 1 year, nearly 10 trillion kilometres. So when we say the Milky Way is 100,000 light-years across, we are describing a distance so large that even light, moving faster than anything else in nature, needs 100 millennia to cross it. And yet the Milky Way is just one galaxy among hundreds of billions. The nearest large galaxy, Andromeda, lies about 2.5 million light-years away. That distance is so great that the light we see from Andromeda tonight began its journey long before humans existed in their modern form. between galaxies, space is mostly empty, but gravity still links these islands of stars into groups and clusters. Our local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, spans roughly 10 million light-years. That might seem immense, and it is, but it is only a small part of a larger structure known as a cluster or supercluster. The Virgo cluster, one of the dominant structures in our region, contains thousands of galaxies and spans tens of millions of light-years. Beyond Virgo lies an even larger arrangement of clusters and groups, extending across hundreds of millions of light-years. These are the structures known as superclusters. But what does it really mean to say that a supercluster is hundreds of millions of light-years across? Numbers alone do not convey the scale very well, so it can help to think in terms of time. If a beam of light began its journey at one edge of a supercluster, when the first dinosaurs were just beginning to appear on Earth, that light might only now be reaching the opposite side. The entire rise and fall of the dinosaurs, the extinction that ended their era, the evolution of mammals, the emergence of humans, the development of language, agriculture, cities, and modern science, all of it would unfold in the time it takes light to cross such a structure. Another way to approach the scale is to think about motion. Galaxies move through space at speeds of hundreds or even thousands of kilometers per second. That sounds extraordinarily fast, and by any ordinary standard it is. Yet even at those speeds, crossing a supercluster would take billions of years. The journey would span a significant fraction of the age of the universe itself. This is why superclusters are not tightly bound objects in the same way that galaxies or clusters are. Their gravity influences the motion of galaxies, guiding large-scale flows, but the expansion of the universe is also at work, gradually stretching space on the larger scales. Some parts of a supercluster may remain gravitationally linked, while others slowly drift apart over cosmic time. When astronomers began to map these enormous structures, they discovered that superclusters are not isolated islands. Instead, they are connected by filaments of galaxies and separated by vast voids. The universe on its larger scales resembles a sponge or a web, with matter concentrated along thin strands and enormous empty regions in between. This cosmic web provides the context for understanding structures like Laniakea and the Great Attractor. They are not isolated giants, but parts of an interconnected system, shaped by gravity over billions of years. One of the challenges in grasping these scales is that our intuition is shaped by everyday experience, where distances are measured in meters or kilometers, and time is measured in minutes or hours. The brain is not naturally equipped to imagine distances measured in millions of light years, so astronomers often rely on comparisons and analogies to make these scales more approachable. Imagine shrinking the Milky Way to the size of a dinner plate. On that scale, the solar system would be smaller than a grain of sand, and the distance to the nearest star would be several meters. Now imagine that dinner plate is just one of many scattered across a continent-sized surface. That begins to hint at the spacing of galaxies within a supercluster. Or consider this. If the entire observable universe were reduced to the size of the Earth, a supercluster would still be comparable to a large country, and a galaxy like the Milky Way would be a small city within it. The solar system would be smaller than a building, and Earth itself would be microscopic. These comparisons are imperfect, of course, but they help anchor the mind, giving it something familiar to hold on to while contemplating the unfamiliar. Another aspect of scale that is easy to overlook is mass. Superclusters contain not only vast numbers of galaxies, but also enormous amounts of dark matter, which outweighs the visible matter by a factor of several times. This dark matter forms halos and filaments that shape the motion of galaxies, guiding them along gravitational pathways. The total mass of a supercluster can be measured in millions of billions of times the mass of the Sun. Such numbers quickly become unwieldy, but they remind us that gravity, though the weakest of the fundamental forces at small scales, becomes dominant when enormous amounts of matter are involved. It is gravity that gives superclusters their structure, pulling matter into filaments and clusters, shaping the flows of galaxies across hundreds of millions of light years, And yet, even gravity has its limits. On the largest scales, the expansion of the universe driven by dark energy gradually overcomes gravitational attraction, causing distant structures to recede from one another. This interplay between gravity and expansion adds another layer to our understanding of scale. Superclusters are not permanent fixtures in the universe. Over billions of years, their shapes and boundaries change. Some regions become more tightly bound, while others drift apart, carried by the expansion of space. There is something quietly poetic in that thought, though perhaps poetic is not quite the right word. It is more a sense of gentle impermanence, a reminder that even the largest structures in the universe are part of an ongoing process, evolving slowly over cosmic time. Returning to the question of how big superclusters really are, it becomes clear that the answer depends on how we define them. If we define them by the distribution of galaxies, their sizes can vary widely, from tens of millions to hundreds of millions of light-years. If we define them by gravitational flows, as in the case of Laniakea, their boundaries become more complex, shaped by the motion of galaxies rather than simple geometry. In either case, the scale is immense beyond ordinary comprehension, and yet, understanding that scale is important because it provides context for everything else we study in astronomy. The motion of galaxies, the formation of clusters, the distribution of dark matter, and the influence of structures like the Great Attractor all make more sense when seen within the vast framework of superclusters. Sometimes it can be calming to reflect on these immense scales. In everyday life, our concerns often feel immediate and pressing, measured in hours or days. But when you consider that galaxies drift for billions of years, that light travels for millions of years to reach us, and that structures hundreds of millions of light-years across evolve at a pace so slow it is almost timeless, there is a certain perspective that emerges. The universe is vast, but it is also patient. Change happens, but slowly. Motion occurs, but gently. Even the largest flows of galaxies are more like the steady movement of a tide than the rush of a storm. And as astronomers continue to study these enormous structures, another question naturally arises. If superclusters are so large and complex, what forces shaped them in the first place? How did matter in the early universe gather into filaments and clusters, eventually forming the vast cosmic web we see today? Long before galaxies gathered into clusters, before superclusters stretched across hundreds of millions of light-years, and even before the first stars began to shine, the universe was a far simpler place. It was hot, dense, and remarkably uniform, filled with a nearly smooth distribution of matter and radiation. If you could have looked across vast distances at that time, you would not have seen the rich cosmic web we know today. You would have seen something much more even, almost featureless, like a calm ocean before the wind begins to shape waves. And yet, hidden within that early smoothness were tiny irregularities, small differences in density so slight that they amounted to only 1 part in 100,000. These variations were not visible to the human eye, but they were enough. Over billions of years, gravity would amplify them, turning slight ripples into galaxies, clusters, and the enormous structures that now shape the motion of matter across the universe. To understand how this happened, it helps to think about gravity in its simplest form. Gravity is the attraction between masses. Every object with mass pulls on every other object. On small scales, this pull can seem weak. A chair does not noticeably attract a table, and a person standing in a room does not feel the gravitational pull of nearby furniture. But gravity has one remarkable property. It never cancels out completely over large distances, and it always adds together. When enough matter gathers, the combined pull becomes powerful enough to shape entire regions of space. In the early universe, matter was spread almost evenly, but not perfectly so. In some regions, there was just a tiny bit more matter than average. Those slightly denser regions exerted a slightly stronger gravitational pull, drawing in more matter from their surroundings. As more matter accumulated, the pull increased further, attracting still more material. This process, called gravitational instability, is the fundamental mechanism by which structure forms in the universe. You can picture it by imagining a wide, shallow landscape after a light rain. At first, water lies evenly across the ground, but small dips begin to collect a little more water than the surrounding areas. As those dips fill, they deepen, attracting even more water. Eventually, small puddles form, then streams, then larger pools. The pattern grows from tiny differences amplified over time. In the universe, gravity plays the role of the slope guiding the flow. One of the most important ingredients in this process is something we cannot see directly: dark matter. Ordinary matter, the atoms that make up stars, planets, and people, accounts for only a small fraction of the universe's total mass. Dark matter outweighs it by several times and interacts primarily through gravity. It does not emit or absorb light, but its presence can be inferred from the way galaxies rotate, from the motion of galaxy clusters, and from the bending of light by gravity. Dark matter began clumping together very early in cosmic history, forming the first gravitational wells. Ordinary matter, still in the form of hot gas, gradually fell into these wells, cooling and condensing until the first stars and galaxies formed. Without dark matter, this process would have been far slower, and the large-scale structure of the universe might look very different. As galaxies formed, they did not remain isolated. Gravity continued to pull them together, forming groups and clusters. Over hundreds of millions of years, clusters themselves began to gather into larger associations, connected by filaments of dark matter and gas. The result was the cosmic web, a vast network of structures extending across the observable universe. Computer simulations have been especially helpful in visualizing this process. By starting with conditions similar to those measured in the early universe and allowing gravity to act over billions of years, scientists can watch virtual universes evolve. In these simulations, small fluctuations grow into filaments, nodes, and voids, producing patterns that closely resemble what we observe through telescopes. Watching these simulations can be strangely calming. Matter flows along invisible pathways, slowly gathering into larger structures. Nothing happens quickly. The timescales are immense, measured in billions of years. Galaxies drift, merge, and reshape themselves, all at a pace that feels almost serene. One of the key insights from these studies is that structure formation is hierarchical. Smaller objects form first, then combine to form larger ones. Stars form within galaxies, galaxies gather into groups, groups merge into clusters, and clusters connect into superclusters. Each level builds upon the previous one, like layers in a gradually growing landscape. Gravity on these scales behaves differently from what we experience in everyday life. On Earth, gravity pulls objects downward toward the ground, and the effect is immediate and obvious. In the universe, gravity operates across distances so vast that its effects unfold over millions or billions of years. The motion is gentle, but persistent. Another important factor shaping large-scale structure is the expansion of the universe. While gravity pulls matter together, expansion pushes distant regions apart. The balance between these two influences determines how structures grow. In regions where gravity dominates, matter collapses into clusters and filaments. In regions where expansion wins, matter becomes more diffuse, forming enormous voids. These voids are some of the largest structures in the universe, vast regions containing very few galaxies. They can span hundreds of millions of light years, making them comparable in size to superclusters. The contrast between dense filaments and empty voids gives the cosmic web its characteristic appearance. As structures grow larger, their influence extends farther. Massive clusters and superclusters create gravitational fields that shape the motion of galaxies over enormous distances. This is the scale at which features like the Great Attractor and the Laniakea basin emerge, not as isolated objects, but as parts of a larger gravitational landscape. It is also worth noting that the formation of structure is still ongoing. Galaxies continue to merge, clusters continue to grow, and matter continues to flow along filaments. The universe is not a finished arrangement, but a dynamic system evolving over time. If you imagine standing far above this cosmic web, watching it evolve in accelerated time, you might see filaments brightening as galaxies gather, clusters swelling as they merge, and voids expanding like bubbles. The motion would be slow but continuous, a quiet reshaping of the universe driven by gravity's steady pull. There is something deeply reassuring in that steadiness. Gravity does not rush. It does not act in sudden bursts. It works patiently, drawing matter together over immense spans of time. Even the largest structures in the universe are built gradually, through countless small steps, each one guided by the same simple law. Returning to the question of how structures like superclusters form, it becomes clear that they are the result of this long process of accumulation and flow. They are not created in a single event, but emerge from the collective motion of countless galaxies, each responding to the gravitational pull of its surroundings. And yet gravity alone does not tell the whole story. On the larger scales, another force comes into play, one that acts in the opposite direction. Dark energy, the mysterious phenomenon driving the accelerated expansion of the universe, gradually stretches space itself, making it harder for gravity to pull distant structures together. Over billions of years, this expansion will isolate clusters and superclusters, leaving them separated by ever-growing distances. This interplay between gravity and expansion gives the universe its evolving structure, shaping not only where matter gathers, but also how long those gatherings remain connected. When astronomers study the Great Attractor and the flows of galaxies around it, they are observing one moment in this vast process, a snapshot of structures still forming, still changing, still responding to the slow dance of gravity and expansion. If gravity shapes the motion of galaxies and the formation of superclusters, how much of that influence comes from matter we cannot see? How much of the pull guiding these vast flows is due to dark matter, the hidden mass that outweighs everything visible? If you are able to watch the motion of galaxies from far above, seeing millions of light years at once the way we see landscapes from an airplane window, one of the first things you might notice is that the visible matter alone does not seem heavy enough to explain what is happening. Galaxies orbit within clusters at speeds that should fling them apart. Clusters themselves drift and tug on one another with a strength that suggests far more mass than telescopes can directly detect. And on the largest scales, vast flows of galaxies, like those leading toward the Great Attractor, move as though guided by an invisible framework, something present but unseen. That invisible framework is what astronomers call dark matter. The name can sound mysterious, even a little dramatic, but the idea behind it is surprisingly simple. Dark matter is matter that does not emit light, does not reflect light, and does not absorb light in any way we can easily detect. It does not shine like stars or glow like hot gas. It simply exists, quietly exerting gravity. To understand why scientists became convinced that dark matter must exist, it helps to return to a much smaller scale, to the motion of individual galaxies. In the early 20th century, astronomers began measuring how stars move within spiral galaxies. According to the laws of gravity, stars farther from the center of a galaxy should orbit more slowly, just as planets farther from the sun move more slowly in their orbits. The gravitational pull weakens with distance, and orbital speeds should decrease accordingly. But when astronomers measured these speeds, they found something unexpected. Stars in the outer regions of galaxies were moving just as fast as stars close to the center. The rotation curves of galaxies were flat, not declining as predicted. This meant that there was far more mass present than could be accounted for by the visible stars and gas. At first, this result was puzzling. Perhaps there were faint stars or cold gas clouds that telescopes were missing. But as observations improved, it became clear that the missing mass was far greater than any ordinary matter could explain. Galaxies appeared to be embedded in enormous halos of unseen material, extending far beyond the visible disk. This unseen material was given a straightforward name: dark matter. Further evidence came from galaxy clusters, enormous gatherings of hundreds or thousands of galaxies bound together by gravity. When astronomers measured how fast galaxies moved within these clusters, they found that the clusters should not be able to hold themselves together if only visible matter were present. The galaxies were moving too fast. Without additional mass, the clusters would disperse over time. Once again, the simplest explanation was that there was far more matter present than could be seen. Gravitational lensing provided another powerful clue. According to Einstein's theory of general relativity, massive objects bend the path of light passing near them. When astronomers observed distant galaxies shining through foreground clusters, they saw the light distorted into arcs and rings, as though passing through a gigantic lens. By measuring the amount of bending, scientists could estimate the mass of the intervening cluster. Time and again, the mass inferred from gravitational lensing was far greater than the mass of visible matter. Something invisible was contributing to the gravitational pull. Taken together, these lines of evidence formed a compelling picture. The universe contains far more matter than we can see, and this dark matter plays a crucial role in shaping the structure and motion of galaxies. Returning to the Great Attractor, the importance of dark matter becomes even clearer. The gravitational pull influencing the motion of galaxies over hundreds of millions of light years cannot be explained by visible galaxies alone. Even enormous clusters like Norma, massive as they are, represent only part of the total mass involved. Surrounding and connecting these clusters are vast halos and filaments of dark matter, forming the backbone of the cosmic web. It may help to imagine the visible galaxies as tiny beads strung along invisible threads. The beads are what we see through telescopes, but the threads, far more massive, determine the overall shape and motion of the structure. Without the threads, the beads would drift apart and the pattern would collapse. Dark matter provides those threads. One of the most remarkable aspects of dark matter is how early it began shaping the universe. In the first few 100,000 years after the Big Bang, ordinary matter was tightly coupled to radiation, prevented from clumping effectively by the intense pressure of light. Dark matter, however, did not interact with radiation in the same way. It began forming gravitational clumps much earlier, creating the first scaffolding of structure. Later, as the universe cooled and ordinary matter could begin to collapse, gas fell into these dark matter wells, eventually forming stars and galaxies. In this sense, dark matter acted as the seedbed of cosmic structure, guiding the formation of everything we now observe. Computer simulations make this process easier to visualize. When scientists model the evolution of the universe, including dark matter, they see filaments and clusters forming in patterns that closely resemble real observations. Without dark matter, those structures do not form in the same way. The universe would look far smoother, with far fewer galaxies and much less large-scale structure. Despite its importance, dark matter remains one of the greatest mysteries in physics. We know it exists because of its gravitational effects, but we do not yet know what it is made of. It does not appear to be composed of atoms or any familiar particles. Instead, scientists suspect it may consist of entirely new types of particles that interact only weakly with ordinary matter. Experiments around the world are searching for these particles, using detectors placed deep underground to shield them from cosmic rays and other interference. These detectors are designed to sense the faintest possible interactions, the tiny signals that might occur if a dark matter particle were to pass through and collide with an atom. So far, the results have been inconclusive. Dark matter remains elusive, detected only through its gravitational influence. Yet that influence is unmistakable, shaping galaxies, clusters, and the vast flows of matter that define structures like Laniakea. There is something quietly intriguing about the idea that most of the matter in the universe is invisible. It reminds us that what we see is only a small part of reality. The night sky, filled with stars and galaxies, is only the luminous surface of a much larger hidden structure. And yet this hidden structure is not mysterious in a frightening way. It does not lurk or threaten. It simply exists, quietly shaping the universe through gravity, guiding the motion of galaxies over billions of years. If you imagine the universe as an ocean, visible matter would be like foam on the waves, bright and ever-changing, while dark matter would be the vast, deep water beneath, unseen but essential, giving shape and motion to everything above. The presence of dark matter also helps explain why galaxies move in large-scale flows. Gravity does not act only from the luminous clusters we can see. It acts from the total mass, including the invisible halos and filaments extending far beyond visible structures. The pull toward the Great Attractor is therefore not the influence of a single object, but the combined effect of enormous amounts of matter, much of it dark. Another important clue about dark matter comes from observations of the cosmic microwave background, the faint afterglow of the early universe. Tiny fluctuations in this radiation reveal how matter was distributed when the universe was only a few 100,000 years old. By analysing these patterns, scientists can determine the total amount of matter present and how much of it must be dark. The results are striking. Ordinary matter, the atoms that make up everything we see, accounts for only about 5% of the universe's total energy and mass. Dark matter makes up roughly 25%, while the rest is dark energy, the mysterious phenomenon driving the accelerated expansion of the universe. So when we speak of the hidden mass behind the pull of the Great Attractor, we're speaking not of a small correction or a minor addition, but of the majority of matter in that region. The galaxies we see are only the luminous markers of a far larger gravitational landscape. Sometimes it can be calming to reflect on the quiet persistence of gravity across these immense scales. The forces shaping the motion of galaxies are not violent or sudden. They act slowly, steadily, over billions of years. The drift of galaxies toward massive structures is more like the slow movement of glaciers than the rush of a storm. Our own galaxy is part of this motion, carried along with countless others through the vast basin of Laniakea. The journey is so gradual that it unfolds far beyond human timescales, yet it is real, guided by the invisible mass that permeates the universe. And as astronomers continue to study these flows, another question naturally arises. If dark matter forms the scaffolding of cosmic structure and superclusters shape the motion of galaxies, is the Great Attractor itself a single structure, or is it part of something even larger still, perhaps only one region within a greater concentration of mass, stretching far beyond what we first imagined? At first, when astronomers began speaking about the Great Attractor, it was tempting to imagine it as a single enormous object, perhaps a gigantic cluster of galaxies, or some unusually dense concentration of matter sitting in one particular location and pulling everything around it inward. The name itself encouraged that picture. An attractor sounds like a point, a destination, something you could circle on a map and say, there it is. But as observations improved and the maps of galaxy motions became more detailed, that simple picture began to fade. What researchers were uncovering turned out to be far more complex, and in some ways, far more interesting. To understand why, it helps to return to the way the Great Attractor was first identified. It was not discovered by directly observing a bright structure in the sky. It was inferred from motion, from the peculiar velocities of galaxies drifting in a common direction. That motion pointed toward a region rather than a precise point, and even early measurements suggested that the gravitational influence extended across a broad area. Imagine standing in a wide valley on a misty morning. You might feel the air gradually cooling as it flows downhill, and you might see streams of water moving in the same general direction. But if the mist hides the landscape, you may not know whether there is a single deep basin ahead, or a series of hills and depressions guiding the flow. The motion tells you something about the shape of the land, but not everything. Astronomers found themselves in a similar situation. The flow of galaxies indicated a gravitational slope, but the exact structure of that slope remained uncertain. As observations penetrated the zone of avoidance and revealed more of the hidden galaxies in that direction, one important structure emerged into clearer view: the Norma cluster. This cluster is enormous, containing hundreds of large galaxies and vast quantities of hot gas and dark matter. Its mass alone is comparable to some of the richest clusters known in the nearby universe. For a time, it seemed possible that the Norma cluster itself might be the Great Attractor, the main source of the gravitational pull affecting our region of space. But further measurements show that this explanation was incomplete. The observed motions of galaxies suggested a gravitational influence even larger than the mass of Norma alone could provide. This realization led astronomers to think of the Great Attractor not as a single object, but as a region of enhanced density, a part of a much larger structure composed of multiple clusters, groups and filaments of dark matter. In other words, it is more like a mountain range than a single peak, more like a basin than a point. One of the reasons this distinction matters is that gravity does not require a single concentrated object to produce large-scale motion. A broad distribution of mass spread across hundreds of millions of light-years can exert a combined pull that shapes the motion of entire superclusters. The Great Attractor appears to be one such region, a convergence of mass whose influence extends across vast distances. As galaxy surveys expanded, astronomers began to see that the flow of galaxies does not simply stop at the Great Attractor. Instead, it continues beyond, toward even larger concentrations of matter. One of the most significant of these is the Shapley supercluster, a massive collection of galaxy clusters located several hundred million light-years farther away. The Shapley supercluster is among the most massive structures in the nearby universe, containing dozens of rich clusters and enormous amounts of dark matter. Its gravitational influence extends across a vast region, and many astronomers now believe that part of the motion attributed to the Great Attractor is actually caused by the combined pull of structures extending all the way to Shapley. This does not mean that the Great Attractor is an illusion or a mistake. Rather, it means that it is part of a larger gravitational landscape, a region where mass is concentrated but not isolated. The flows of galaxies we observe are shaped by multiple influences, some nearer, some farther, all contributing to the overall motion. To visualize this, it can help to think about rivers flowing across a continent. A river may appear to flow toward a nearby lake, but that lake may itself drain into a larger basin farther downstream. The motion of water is guided by the entire shape of the land, not just by one feature. In the same way, galaxies move along gravitational slopes shaped by the combined mass of many structures. Another important factor in understanding the Great Attractor is the concept of gravitational basins, which we discussed earlier in the context of Laniakea. A basin is defined not by sharp edges but by the flow of matter within it. Galaxies inside a basin drift toward a common region, while galaxies outside it drift in different directions. The Great Attractor lies within such a basin, acting as one of the major centers toward which galaxies flow. But it is not necessarily the final destination of that flow, nor is it the only source of gravitational influence. Observations of large-scale galaxy motions continue to refine this picture. Modern surveys, combining redshift measurements with distance indicators, allow astronomers to trace the paths of galaxies across hundreds of millions of light-years. These maps show streams of galaxies converging toward regions of high density, forming patterns that resemble rivers feeding into larger and larger basins. Computer simulations provide further insight. When scientists model the growth of structure in the universe, including the effects of dark matter and dark energy, they find that mass tends to accumulate in extended regions rather than in isolated points. Clusters form along filaments. Filaments intersect to form superclusters, and these structures together create a network of gravitational influences. In such a network, the idea of a single, dominant object becomes less meaningful. What matters is the distribution of mass across large volumes of space. The Great Attractor is best understood as a particularly dense node within this network, one of several regions shaping the motion of galaxies in our part of the universe. There is also the question of time. The structures we observe today are not static. Over billions of years, clusters merge, filaments shift, and gravitational influences change. The Great Attractor itself may evolve, becoming part of even larger structures as matter continues to flow along the cosmic web. This sense of gradual change is an important reminder that the universe is dynamic, even on the largest scales. The motions we observe today are snapshots of an ongoing process, one that began with tiny fluctuations in the early universe and continues to unfold over cosmic time. It is interesting to reflect on how our understanding of the Great Attractor has evolved. At first, it was a mysterious point, inferred from the motion of galaxies but hidden from view. Then it became associated with specific clusters like Norma, and now it is seen as part of a larger system, a region within a vast gravitational landscape extending across hundreds of millions of light years. This progression is typical of science. Early discoveries often simplify complex realities, providing names and concepts that help organize observations. As more data becomes available, those concepts become more nuanced, revealing deeper layers of structure and connection. In a way, this mirrors how we come to understand any landscape. A traveller might first notice a single hill in the distance. Later, climbing that hill, they might see a whole range of mountains beyond it, and beyond those, still larger ranges stretching to the horizon. Each new vantage point reveals a broader perspective. There is something quietly comforting in that gradual unfolding of knowledge. The universe does not reveal all its secrets at once. It invites us to look more closely, to measure more carefully, to think more deeply, and in doing so, it rewards patience with understanding. When we consider whether the Great Attractor is a single object or something much larger, the answer seems to be that it is both less and more than a single object. Less, because it is not a solitary giant dominating its surroundings. More, because it is part of an immense network of mass and motion, extending far beyond what early astronomers imagined. If the Great Attractor is only one part of a larger gravitational landscape, what lies beyond it? What structures farther away contribute to the motion of galaxies in our region? And how far does this chain of influence extend across the universe? Far beyond the region astronomers first associated with the Great Attractor, farther still in the same broad direction of the sky, lies an even more massive and influential structure, something so large that it reshaped how scientists think about motion on the grandest scales. This immense gathering of matter is known as the Shapley concentration, or sometimes the Shapley supercluster, and in many ways it represents the deeper layer of the story, the reason the flow of galaxies does not simply stop at the Great Attractor, but continues onward across hundreds of millions of light years. To understand why this discovery mattered so much, it helps to return to the puzzle astronomers were trying to solve. Measurements of galaxy motions showed that entire regions of space were drifting in a particular direction, carried along by gravitational influences. The Great Attractor appeared to account for part of that motion, especially within the Laniakea basin, but careful analysis suggested that something even larger might be contributing to the pull. Imagine again the idea of rivers flowing through a landscape. If you stand beside a tributary, you might assume the nearby lake is the final destination of the water, but if you follow the current long enough, you may discover that the lake itself feeds into a much larger river, and that river eventually reaches the sea. The motion you first observed was only part of a longer journey. Astronomers began to suspect that the Great Attractor might be similar, not the ultimate source of gravitational influence in our region, but one step along a larger chain of mass concentrations. The evidence came from increasingly detailed maps of galaxy distributions and velocities, which revealed that the flow of matter extended beyond the Great Attractor toward a region much farther away. The Shapley concentration lies roughly 600 to 700 million light-years from Earth, more than twice the distance to the Great Attractor region. Even by the standards of superclusters, it is extraordinarily massive, containing dozens of rich galaxy clusters packed into a relatively small volume of space. The total mass of this structure is immense, enough to exert a measurable gravitational influence across hundreds of millions of light-years. What makes the Shapley concentration especially remarkable is not only its size, but also its density. Many superclusters are sprawling and loosely connected, with clusters spread across large distances. Shapley, by contrast, contains a particularly dense core, where multiple massive clusters lie in close proximity. This concentration of mass creates a gravitational well deeper than most structures in the nearby universe. When astronomers first began to map this region in detail, they realized that the gravitational pull of Shapley could help explain why galaxy flows appeared stronger than the Great Attractor alone could account for. The motion of galaxies, including our own Milky Way, is influenced not just by nearby structures, but by the combined pull of many regions, some closer, some farther away, all contributing to the overall pattern. It can be helpful to think of gravity in this context not as a single tug from one direction, but as a gentle slope shaped by many hills and valleys. A nearby hill may dominate your immediate surroundings, but a distant mountain range can still influence the overall shape of the landscape. In the same way, the Great Attractor represents a significant feature in the gravitational terrain, while the Shapley concentration forms part of an even larger rise beyond it. The discovery of Shapley itself is an interesting story. The structure is named after the astronomer Harlow Shapley, who in the early 20th century studied the distribution of globular clusters in the Milky Way and helped determine our galaxy's true size and the Sun's position within it. The concentration bearing his name was identified later as astronomers conducted deeper surveys of galaxy clusters in the southern sky. At first, these surveys revealed a surprising number of rich clusters in one region, more than expected from a random distribution. As additional observations were made, it became clear that these clusters were not isolated but part of a single enormous structure. Redshift measurements showed that they lay at similar distances, confirming that they formed a coherent supercluster. Mapping the Shapley concentration required the same techniques used to study other large-scale structures: measuring redshifts to determine velocities, estimating distances through standard candles and other methods, and constructing three-dimensional maps of galaxy distributions. Over time, the picture that emerged was one of a massive knot in the cosmic web, a place where filaments converge and matter accumulates. The role of dark matter in this structure is, of course, essential. Visible galaxies account for only a fraction of the total mass. Surrounding and connecting the clusters are enormous halos of dark matter, extending far beyond what telescopes can see. These halos deepen the gravitational well, increasing the pull felt by galaxies across vast distances. Another piece of evidence for Shapley's influence comes from studies of galaxy flows in the local universe. By measuring the peculiar velocities of galaxies and tracing their motion relative to the cosmic microwave background, astronomers can determine the direction and magnitude of large-scale flows. These studies suggest that a significant portion of our motion through space may be influenced by the combined pull of both the Great Attractor and the Shapley concentration. This does not mean that galaxies are on a direct path toward Shapley, nor that they will ever reach it. The expansion of the universe and the immense distances involved make such journeys unlikely on practical timescales. Instead, the influence is more subtle, shaping the overall direction of motion rather than determining a precise destination. It is interesting to reflect on how long these gravitational interactions take to unfold. Light from the Shapley concentration has been travelling for hundreds of millions of years before reaching us. The gravitational influence we feel today began affecting our region of space long before the first dinosaurs walked the Earth. The motions we observe are part of processes that span vast stretches of time, far beyond anything in human history. There is something calming in that perspective. The universe moves slowly on its larger scales. Galaxies drift rather than rush, guided by forces that act patiently over billions of years. Even the pull of something as massive as the Shapley concentration is gentle when experienced across such distances, more like the steady movement of a tide than the sudden force of a wave. The realization that the Great Attractor is not the final step in this chain of influence also changed how astronomers think about superclusters in general. Instead of viewing them as isolated islands of matter, scientists now see them as parts of a continuous network, connected by filaments and shaped by flows of galaxies moving along gravitational gradients. This network, often called the cosmic web, extends across the observable universe. On its largest scales, matter forms a pattern of filaments and nodes separated by enormous voids. Superclusters like Laniakea and Shapley are among the largest nodes in this web, places where many filaments intersect and matter accumulates. Computer simulations of cosmic structure formation help illustrate how such massive concentrations arise. Starting with the tiny fluctuations in density present in the early universe, gravity gradually amplifies these differences, drawing matter into filaments and clusters. Over billions of years, some regions become particularly dense, forming structures like the Shapley concentration. Watching these simulations unfold is rather like watching frost patterns spread across a window pane, delicate filaments branching and merging, gradually forming intricate designs. The process is slow and steady, guided by simple physical laws, yet the result is astonishingly complex. Another intriguing aspect of the Shapley concentration is its role in defining the boundaries of gravitational basins like Laniakea. The flow of galaxies within a basin is determined by the distribution of mass around it. If a sufficiently massive structure lies beyond the basin, it can influence the direction of flow, effectively shaping the watershed between different regions. In this sense, the Great Attractor and the Shapley concentration are part of the same gravitational landscape, one nearer, one farther, both contributing to the motion of galaxies across hundreds of millions of light years. It is worth remembering that our understanding of these enormous structures is still evolving. New surveys continue to map galaxy distributions in greater detail, revealing previously unknown clusters and refining measurements of galaxy velocities. Each new dataset adds depth to the picture, helping astronomers better understand how mass is distributed on the larger scales. Future telescopes and surveys will likely uncover even more distant and massive structures, extending our maps of the cosmic web farther into the universe. The story of the Great Attractor and the Shapley concentration may turn out to be only one chapter in a much larger narrative about the distribution of matter across cosmic time. For now, what we know is already remarkable. Our galaxy, along with countless others, moves within a vast gravitational landscape shaped by structures so large that light takes hundreds of millions of years to cross them. The Great Attractor is part of that landscape, and beyond it lies the Shapley concentration, an even deeper well in the fabric of space, contributing to the slow, steady drift of galaxies across the universe. And as we continue to follow this chain of influence outward, another question naturally comes to mind. If these immense structures shape the motion of galaxies, how fast is our own galaxy actually travelling through space? And what does that motion mean when viewed against the vast backdrop of the cosmic web? At any given moment, it can feel as though we are perfectly still. Sitting in a chair, lying in bed, or resting quietly, the world around us seems steady and unmoving. The walls do not shift, the floor does not drift, and the air feels calm. Yet this sense of stillness is one of the most convincing illusions in everyday life. Even on Earth, we are never truly at rest. The planet spins, carrying us around its axis at hundreds of meters per second. It orbits the Sun at about 30 kilometers per second. And beyond that, the Sun itself moves through the Milky Way, while the Milky Way travels through the universe as part of a much larger cosmic flow. When we ask how fast the Milky Way is travelling, the answer depends on what we mean by motion, because there is no single universal frame of reference in which everything stands still. Motion in the universe is always measured relative to something else, so astronomers begin by choosing a reference that is as close to universal as possible: the cosmic microwave background, the faint radiation left over from the early universe. This radiation fills all of space and appears almost perfectly uniform in every direction, but not quite perfectly. Careful measurements show a slight temperature difference between one side of the sky and the other. One direction appears a tiny bit warmer, and the opposite direction a tiny bit cooler. This difference is not because the universe itself is warmer in one direction, but because we are moving through this sea of radiation. As we travel, radiation in the direction of motion is slightly blue-shifted, while radiation behind us is slightly red-shifted. By measuring this effect, astronomers can determine both the speed and the direction of our motion relative to the cosmic microwave background. The result is remarkable. The Milky Way, along with our neighbouring galaxies, is moving at about 600 kilometers per second relative to this cosmic reference frame. That is more than 2 million kilometers per hour. To give that speed some perspective, consider that at 600 kilometers per second, you could travel from Earth to the Moon in less than 11 minutes. You could cross the entire diameter of the Earth in about 20 seconds. Yet even at that speed, crossing the Milky Way galaxy would take more than 150 million years. Space is vast beyond ordinary imagination, and even extraordinary speeds feel slow on cosmic scales. This motion is not random. It is the result of gravitational influences acting over enormous distances. Nearby structures such as the Virgo cluster contribute part of the pull. The region associated with the Great Attractor contributes more. And farther still, massive concentrations like the Shapley supercluster exert additional influence. The Milky Way is part of a vast network of galaxies drifting along gravitational currents shaped by these immense structures. It is interesting to think of this motion not as a straight-line journey, but as a layered set of movements, each one superimposed on the others. The Earth rotates, the Earth orbits the Sun orbits the centre of the Milky Way, and the Milky Way itself moves through intergalactic space. Each of these motions has its own speed and direction, and together they form a complex trajectory through the universe. The Sun, for example, orbits the centre of the Milky Way at about 220 kilometers per second. One complete orbit, sometimes called a galactic year, takes roughly 230 million Earth years. That means the Sun has completed only about 20 such orbits since it formed, and only a fraction of one orbit since the dinosaurs roamed the Earth. Meanwhile, the Milky Way and the Andromeda Galaxy are moving toward one another at about 110 kilometers per second, drawn together by their mutual gravity. In about 4 to 5 billion years, they're expected to merge, forming a single larger galaxy. This future event will unfold slowly, over hundreds of millions of years, with stars passing one another at vast distances, making direct collisions unlikely, but reshaping the overall structure of the galaxies involved. These local motions are part of a larger pattern. The local group of galaxies moves toward the Virgo cluster at several hundred kilometers per second, and beyond that, the entire region, including the Virgo cluster itself, drifts toward the Great Attractor and the broader gravitational basin of Laniakea. If you imagine all these motions combined, it can feel a bit like standing on a moving walkway inside a train that is itself travelling along a curved track on a rotating planet. Each motion is real, but none is felt directly because everything around you shares the same movement. One of the reasons we do not feel these enormous speeds is that motion at constant velocity produces no sensation. Only acceleration can be felt, and the accelerations involved in cosmic motions are extremely small. The gravitational pulls guiding galaxies are gentle, spread over vast distances, so the resulting accelerations are tiny compared with those we experience in everyday life. Another way astronomers measure the motion of galaxies is by studying their redshifts and peculiar velocities, as we discussed earlier. By comparing the observed velocity of a galaxy with this velocity expected from cosmic expansion, scientists can determine how much of its motion is due to gravitational influences. When these measurements are made for thousands of galaxies, patterns emerge, revealing large-scale flows across the universe. These flows are sometimes visualized as streams, with galaxies represented as points moving along curved paths toward regions of greater mass. The Milky Way appears as one participant in this vast motion, carried along by the gravitational landscape shaped by clusters, superclusters, and dark matter filaments. There is something quietly reassuring in this picture. The universe is not chaotic on its larger scales. It has structure, patterns, and flows that can be traced and understood. Even though the distances are immense and the timescales almost beyond comprehension, the same physical laws apply everywhere, guiding the motion of galaxies just as they guide the fall of an apple or the orbit of the moon. It is also worth reflecting on how long these motions take to produce noticeable changes. At 600 kilometers per second, the Milky Way travels about 19 billion kilometers in a year, which sounds enormous until you compare it with intergalactic distances. The nearest large galaxy, Andromeda, lies about 2.5 million light-years away, a distance so vast that even travelling at our current speed, it would take billions of years to cross. This immense scale gives cosmic motion a sense of calm continuity. Nothing happens quickly. Galaxies drift rather than rush, guided by forces that act patiently over billions of years. The journey of the Milky Way through space is not a dramatic plunge, but a slow and steady glide, part of a larger flow that has been unfolding since long before our Sun formed. Another fascinating aspect of our motion through space is that it provides clues about the distribution of mass in the universe. By measuring how fast galaxies move and in what direction, astronomers can infer where the gravitational pull must be coming from, even when the sources of that pull are hidden or distant. In this way, the motion of the Milky Way becomes a kind of probe, revealing the structure of the universe on the larger scales. The cosmic microwave background plays a key role in this process because it provides a universal reference frame. Without it, measuring our motion would be far more difficult. The slight temperature differences across the sky act like a cosmic wind indicator, showing the direction in which we are moving and the speed of that motion. It can be calming to imagine that background radiation filling all of space, a faint afterglow from the early universe, nearly uniform in every direction. Against that backdrop, the Milky Way moves quietly, one galaxy among billions, drifting through a vast and ancient cosmos. As we continue to map these motions in greater detail, astronomers gain a clearer picture of the large-scale structure of the universe and the forces shaping it. The flows of galaxies, the influence of dark matter, and the distribution of massive structures all become part of a coherent story, one that connects our own galaxy to regions hundreds of millions of light-years away. Much of what we know about these immense structures comes from indirect evidence, from motions and measurements rather than direct images. So what would the sky actually look like if we could see the Great Attractor and the surrounding structures clearly, without the dust of the Milky Way blocking our view, without the limitations of visible light? If the sky were suddenly cleared of every obstacle that limits our view, the experience would be both breathtaking and strangely unfamiliar. The night sky we know, beautiful as it is, shows only a fraction of what is truly there. Dust within the Milky Way blocks vast regions from sight. The sensitivity of our eyes limits us to a narrow range of brightness and colour. Even the best telescopes capture only selected portions of the electromagnetic spectrum at a time. So the sky we see is, in a sense, an edited version of reality, a filtered glimpse of a much richer and more complex scene. Now imagine, just for a moment, that those limits were lifted. Imagine that the dust of our galaxy became transparent, that your eyes could perceive every wavelength of light from radio to X-ray, and that distance itself no longer dimmed the glow of galaxies to invisibility. The sky would not look empty or sparse. It would appear crowded, layered, alive with structures that are usually hidden from us. One of the first changes you might notice would be the Milky Way itself. Instead of a soft, pale band, it would become an intricate tapestry of stars, glowing gas clouds, and dark filaments. Regions that appear as dark rifts to us now, where dust obscures the light behind, would instead reveal enormous star fields and distant galaxies shining through. The zone of avoidance would no longer be a zone of anything. It would simply be another richly populated region of the universe, filled with clusters and filaments stretching far beyond our own galaxy. Some of those distant structures would appear faint and small, but others would stand out clearly, including the galaxy clusters that make up the region of the Great Attractor. The Norma cluster, for example, would be visible as a dense gathering of galaxies, hundreds of glowing spirals and ellipticals bound together in a gravitational dance. Surrounding it, you would see additional clusters and filaments, forming a network that extends across tens and hundreds of millions of light years. The sky would no longer feel like a flat dome sprinkled with isolated points of light. It would feel deep, layered, almost three-dimensional, with structures overlapping and receding into the distance. Some galaxies would appear near and bright, others faint and far away, forming patterns that hint at the larger cosmic web. Another difference would be the presence of hot gas in galaxy clusters. This gas, heated to millions of degrees, emits strongly in X-rays, which our eyes cannot see. If we could perceive that radiation, clusters would glow with a diffuse halo, revealing the enormous reservoirs of matter that bind galaxies together. The Great Attractor region would not be a single bright point but a broad luminous area, shimmering with the combined emission of many clusters and the hot gas between them. Dark matter, of course, would remain invisible, but its effects might still be sensed indirectly. Gravitational lensing, the bending of light by massive objects, would distort the appearance of more distant galaxies, stretching them into arcs and rings around massive clusters. If you could see these distortions in real time, the sky might look subtly warped in certain directions, as though the fabric of space itself were gently bending. One of the most striking changes, though, would be the sheer number of galaxies visible. In a truly clear and sensitive view, the sky would be filled with them, not just a few thousand, but millions, each one a vast system of stars. Some would appear as delicate spirals, others as smooth ellipses, and still others as irregular shapes glowing softly against the darkness. The emptiness between stars that we perceive now would give way to a sense of abundance, a reminder that the universe is far more populated than it seems. The Great Attractor itself would not look like a single object, because it is not one. Instead, you would see a broad region where galaxies become more numerous, where clusters gather more closely, where the glow of hot gas and the density of structures hint at the immense mass present there. Beyond it, still farther away, the Shapley concentration would appear as an even richer gathering of clusters, a distant but unmistakable knot in the cosmic web. If you could watch the sky over extremely long periods of time, another layer of motion would become apparent. Galaxies would not remain fixed. They would drift slowly relative to one another, their positions changing over millions of years. The motion would be far too slow to notice in a single night, but in an accelerated view, the sky would resemble a vast current, with galaxies flowing along filaments toward denser regions. This idea of motion is important, because it reminds us that the universe is not static. The structures we see today are the result of billions of years of evolution, and they continue to change. Clusters merge, galaxies interact, and the large-scale flows of matter gradually reshape the cosmic landscape. There is also the matter of brightness. If distance did not dim light, the night sky would not be dark at all. It would glow in every direction, filled with the combined light of countless galaxies. The darkness we see is partly a result of the vast distances between us and most of the luminous matter in the universe. Remove that dimming, and the sky would shine with a soft, continuous radiance. Of course, such a sky would be overwhelming to human senses. Our eyes and brains are adapted to a much narrower range of brightness and detail. Part of what makes the night sky so calming is its simplicity, the gentle contrast between stars and darkness, the quiet spaces between points of light. A sky filled with millions of galaxies might feel less peaceful, more like standing in a brightly lit city than under a tranquil canopy of stars. And yet, there is another way to imagine seeing clearly, one that preserves the calm while revealing the hidden structure. Instead of making everything brighter, imagine being able to see the underlying patterns, the filaments of galaxies stretching across space, the basins where galaxies drift together, the gentle slopes of gravity shaping the motion of matter. The sky would not be crowded so much as connected, every galaxy part of a larger design. Astronomers, in a sense, already see the universe this way, not with their eyes alone, but through maps and simulations. When they plot the positions of galaxies in 3 dimensions, a remarkable pattern emerges. Galaxies trace out long filaments, intersecting at dense nodes and surrounding vast voids. The Great Attractor region appears as one of these nodes, part of a network that extends across hundreds of millions of light years. Looking at these maps can be a strangely calming experience. The structures resemble delicate threads, like frost patterns on glass, or the branching of rivers seen from high above. There is a sense of order, of quiet balance, of gravity shaping the universe with patient precision. Another aspect of seeing clearly would be the ability to perceive different wavelengths simultaneously. Radio waves would reveal vast clouds of hydrogen gas stretching between galaxies. Infrared light would show regions of star formation hidden within dust. Ultraviolet light would highlight young, hot stars, while X-rays would trace the hottest and most energetic environments. The sky would become a layered tapestry, each wavelength adding a different piece of information. In such a view, the Great Attractor would not be mysterious in the way it once was. Its mass distribution, its clusters, its surrounding filaments would all be visible, mapped out in detail. The flows of galaxies toward it would be easier to understand, because the gravitational landscape would be laid bare. There is something comforting in knowing that even when we cannot see something directly, it can still be understood. The Great Attractor was discovered not by sight, but by inference, by tracing the motion of galaxies and piecing together clues from many different observations. In a way, this makes the discovery even more satisfying, because it shows how much can be learned through careful reasoning and patient study. It is also a reminder that perception is always limited. Every living creature experiences only a small part of reality, filtered through its senses. Humans see only a narrow band of light, hear only a limited range of sound, and perceive time on a scale of seconds and years, rather than millions or billions of years. Yet through science, we have found ways to extend those senses, to build instruments that reveal what lies beyond our natural perception. So when we imagine what the sky would look like if we could see it clearly, we're really imagining the universe as it is, rather than as it appears to us. A universe filled with galaxies, shaped by gravity, connected by filaments, and evolving slowly over cosmic time. There is a quiet beauty in that vision, not dramatic or overwhelming, but steady and vast, like an ocean stretching beyond the horizon. The Great Attractor becomes just one feature in that immense landscape, important but not isolated, part of a network that extends far beyond anything we can see from Earth with the naked eye. And as we picture that landscape, another thought naturally arises. These structures, immense as they are not permanent. The universe continues to expand, and over billions of years the distances between superclusters will grow. The flows of galaxies will change, and the gravitational basins we see today may evolve in ways that are difficult to imagine. If the Milky Way and its neighbouring galaxies are drifting through this vast landscape, guided by gravity and shaped by cosmic expansion. What will happen in the far future? Will we ever reach the Great Attractor, or will the expansion of the universe carry us along a different path altogether? It is natural, after hearing about the steady drift of galaxies and the immense pull of structures like the Great Attractor, to wonder whether this motion has a destination. If our galaxy is moving in that direction, if entire regions of space seem to flow along gentle gravitational slopes, does that mean we are on a long journey towards some distant point? And if so, will we ever arrive there, given enough time? At first glance, it might seem reasonable to imagine that we will. After all, gravity pulls objects together. Planets fall towards stars, stars orbit within galaxies, and galaxies merge with one another. These processes feel familiar because they unfold on timescales we can grasp, millions or billions of years, but still within the lifetime of the universe as we know it. So it is tempting to extend that intuition outward and picture the Milky Way gradually drifting closer and closer to the Great Attractor, perhaps eventually becoming part of whatever vast structure lies there. But the universe on the larger scales behaves in ways that differ from our everyday experience. The key factor is not gravity alone, but the expansion of space itself, a process that becomes more important the farther apart objects are. To understand this, it helps to think about what cosmic expansion really means. Galaxies are not simply flying apart through empty space like fragments from an explosion. Instead, the space between galaxies is stretching. Imagine a loaf of bread rising in an oven, with raisins embedded in the dough. As the dough expands, the raisins move farther apart, not because they are moving through the dough, but because the dough itself is stretching. This expansion was discovered nearly a century ago and has since been measured with increasing precision. More recently, astronomers have learned that the expansion is not slowing down, as once expected, but accelerating. This acceleration is attributed to a mysterious phenomenon called dark energy, which appears to make up most of the energy content of the universe. Dark energy acts in a way that opposes gravity on very large scales. While gravity pulls matter together, dark energy causes the expansion of space to speed up, gradually increasing the distances between objects that are not gravitationally bound. This interplay between gravity and expansion determines the future of cosmic motion. On small scales, gravity dominates. The Earth remains bound to the Sun remains bound to the Milky Way, and the Milky Way and Andromeda will eventually merge because their mutual gravity is strong enough to overcome the expansion of space between them. On larger scales, however, the situation changes. Superclusters are not always gravitationally bound as single units. Some parts may remain connected, while others slowly drift apart as expansion stretches the fabric of space. So when we ask whether we will ever reach the Great Attractor, the answer depends on the balance between its gravitational pull and the expansion of the universe. Current evidence suggests that while our galaxy is moving in that general direction, the expansion of space is likely to prevent us from ever actually arriving there. The distances involved are enormous, and the rate of expansion increases with distance. Over billions of years, galaxies that are not tightly bound to one another will drift farther apart, their separation growing faster than gravity can close the gap. In practical terms, this means that the Milky Way and many of its neighbouring galaxies will remain part of the same local structures, but regions hundreds of millions of light years away will gradually recede beyond reach. The Great Attractor, rather than becoming a destination, will remain a distant influence, shaping motion but never fully drawing us in. There is something quietly profound in this idea. The motion of galaxies is real, but it is not a journey in the usual sense. It has direction and speed, but not necessarily an endpoint. The universe is not a closed landscape where everything eventually gathers in one place. It is an evolving, expanding system where some structures merge while others drift apart. To picture this, imagine a wide, slow-moving river that gradually widens into a vast estuary. The current still flows, but the water spreads out and distant shores move farther away. The motion continues, but the sense of approaching a single destination fades. Astronomers study the future of cosmic motion using computer simulations that model the effects of gravity and dark energy over billions of years. These simulations suggest that in the far future, our local group of galaxies will merge into a single large galaxy, sometimes called Milky Way. This merged galaxy will remain bound to a small number of nearby galaxies, forming a stable island of matter. Beyond that island, however, other galaxies and clusters will recede, carried away by the accelerating expansion of space. Over tens or hundreds of billions of years, the observable universe from our perspective will grow emptier, with distant structures fading from view as their light becomes increasingly redshifted and faint. From that distant future viewpoint, the Great Attractor and even the Shapley concentration may no longer be visible at all, their light stretched and dimmed beyond detection. The vast cosmic web we see today will appear fragmented, with only nearby structures remaining observable. This does not mean that those structures will cease to exist. They will still be there, separated by distances so great that communication or travel between them becomes effectively impossible. The universe will become a collection of isolated regions, each evolving largely on its own. It can be calming in a way to reflect on how slowly these changes unfold. The timescales involved are so immense that they dwarf the entire history of humanity. Even the merging of the Milky Way and Andromeda, one of the most dramatic events in our galaxy's future, will take billions of years to begin and hundreds of millions more to complete. The motion toward the Great Attractor, measured in hundreds of kilometers per second, is gentle on such timescales. Over the next few billion years, our galaxy will move only a fraction of the distance required to approach that region significantly. Long before any hypothetical arrival, the expansion of the universe will have altered the larger scale environment in ways that make the question of arrival less meaningful. There is also the question of perspective. When we speak of travelling toward the Great Attractor, we're using language shaped by everyday experience, where motion usually implies a destination. But in the universe, motion often reflects the shape of the gravitational landscape rather than a path to a specific point. Galaxies drift along slopes and flows, influenced by multiple structures at once, their trajectories shaped by the combined effects of gravity and expansion. Our own galaxy's motion is the result of many influences: the pull of nearby clusters, the broader flow within Laniakea, the distant mass of the Shapley concentration, and the expansion of space itself. It is a complex, evolving path rather than a straight line toward a single object. Another important factor is time itself. The universe is about 13.8 billion years old, and the larger structures have taken most of that time to form. The processes shaping cosmic motion operate over spans so long that even entire galaxies can change dramatically, while drifting only modest distances relative to one another. If you imagine watching the universe in accelerated time, you would see galaxies merging, clusters forming, and the cosmic web slowly evolving. But you would also see the expansion of space gradually stretching the distances between large structures, like dough rising and pulling embedded raisins farther apart. The future of cosmic motion is therefore a balance between gathering and dispersal, between gravity pulling inward and expansion pushing outward. On small scales, gathering wins. On the larger scales, dispersal gradually takes over. This perspective can feel strangely peaceful. The universe is not rushing toward a final collision or collapse, at least not according to current understanding. Instead, it is unfolding slowly, with regions of matter forming stable structures while the larger fabric of space continues to expand. So will we ever reach the Great Attractor? Almost certainly not in the literal sense. Our galaxy will continue to move within the gravitational flows of our region, but the expansion of space and the immense distances involved mean that the Great Attractor will remain far away, an influence rather than a destination, and perhaps that is fitting. The Great Attractor is not a place to be reached, but a reminder of the vast structures shaping the universe, a sign of the invisible mass and gentle currents that guide galaxies across unimaginable distances. For a moment, it may help to set aside the immense distances and enormous timescales we've been exploring and simply notice where you are right now. Perhaps you're sitting or lying comfortably, the room quiet, the sounds of the day fading into the background. The world around you feels still, and in a very real sense it is. The chair beneath you is not moving in any way you can feel. The walls are steady. The air is calm. And yet, gently, almost impossibly, everything is in motion. The Earth is turning beneath you, carrying you eastward at hundreds of meters per second, though the motion is so smooth that it feels like stillness. At the same time, the Earth is orbiting the Sun at about 30 kilometers per second, tracing a path that will not quite close because the Sun itself is moving. The Sun, along with all its planets, is orbiting the center of the Milky Way, taking more than 200 million years to complete a single circuit. And the Milky Way in turn drifts through the universe, carried along in a vast flow shaped by gravity on scales so large they are difficult to hold in the mind all at once. All of this motion is happening now, quietly, continuously, without any sensation of speed or wind or vibration. The universe moves with extraordinary smoothness. There is no rushing sound, no trembling, no feeling of acceleration. Motion at constant velocity is indistinguishable from rest, and so the greatest journeys in the cosmos pass unnoticed by those who travel within them. There is something deeply calming about that idea. The universe is not a violent place most of the time. It is patient. Galaxies drift rather than rush. Gravity shapes structures slowly over billions of years. Even the formation of clusters and superclusters unfolds at a pace so gradual that entire civilizations would rise and fall without perceiving a meaningful change in the sky. When astronomers first discovered that our galaxy is moving toward a region known as the Great Attractor, it might have sounded dramatic, almost ominous, as though we were being pulled toward something overwhelming. But as we have seen, the reality is quieter and far more expansive. The Great Attractor is not a single looming object waiting ahead. It is part of a vast gravitational landscape, one feature among many in the cosmic web, influencing motion gently across immense distances. And beyond it lie still larger structures, like the Shapley concentration, reminding us that every time we think we have reached the larger scale, there is another layer beyond, another pattern, another flow extending farther into space. It is easy, when hearing about these enormous structures, to feel small. Our planet is tiny compared with the Sun. The Sun is small compared with the Milky Way. And the Milky Way itself is only one galaxy among billions. On the scale of superclusters, even galaxies begin to seem like grains of sand. But small does not mean insignificant. A single grain of sand can still be warm in sunlight, still be touched by the tide, still be part of the shore. In the same way, our small planet is part of the universe in a very real and immediate sense. The atoms in your body were formed in stars long before the Earth existed. The oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was forged in the hearts of ancient stars and scattered across space before gathering into new systems like our own. So when we speak of our place in the universe, we are not speaking of something separate or distant. We are part of the same story, part of the same long unfolding of matter and energy, shaped by the same physical laws that guide the motion of galaxies. It can be comforting to reflect on how steady those laws are. Gravity does not change from one day to the next. The speed of light remains constant. The same processes that formed galaxies billions of years ago continue to operate today. The universe is vast and complex, but it is also orderly and consistent, governed by principles that can be understood and described. That sense of order is one of the reasons astronomy can feel so calming. Looking at the night sky, or even imagining the larger structures beyond what we can see, invites a kind of quiet perspective. The worries of a single day, or even a single lifetime, become small against the backdrop of billions of years. Problems that feel overwhelming in the moment begin to soften when placed in a wider frame. This does not mean that everyday concerns are unimportant. They are part of our lives, just as the motion of the Earth is part of the larger motion of the galaxy. But perspective can make those concerns feel lighter, easier to hold. Another gentle thought to consider is how slowly the universe changes on human timescales. The stars you see tonight will look almost exactly the same tomorrow, next year, and even centuries from now. The constellations shift gradually over tens of thousands of years, but the change is so slow that generations pass without noticing. The Milky Way will continue its quiet drift, and the flows of galaxies will continue long after all of us are gone, just as they began long before we were here. There is a certain peace in knowing that not everything depends on us, that the universe carries on in its vast, steady way regardless of human concerns. We are participants in that larger story, but we are not responsible for guiding it. The galaxies do not need our help to move, and gravity does not require our attention to continue its work. At the same time, there is something remarkable about the fact that we can understand any of this at all. From a small planet orbiting an ordinary star, human beings have learned to measure the motion of galaxies hundreds of millions of light years away. We have mapped the cosmic microwave background, traced the distribution of dark matter, and discovered structures like Laniakea and the Great Attractor, not by travelling there, but by observing carefully and thinking deeply. That ability to understand, to ask questions and seek answers, is one of the most extraordinary things about being human. The universe is vast, but it is also knowable, at least in part. Each discovery adds a little more clarity, a little more detail to the picture, and yet, even as we learn more, the universe remains a place of quiet mystery. Dark matter still eludes direct detection. Dark energy remains one of the greatest puzzles in physics. The ultimate fate of the cosmos is still being studied and debated. There is always more to discover, more to understand. Perhaps that is part of what makes the universe feel so inviting. It is not a finished story, but an unfolding one, and we are living within it. If you imagine the motion of the Milky Way now, drifting through space, it may help to picture a leaf floating on a slow, wide river. The leaf does not control the current, but it is carried gently along, turning slowly, reflecting the sky above. The river moves steadily, not rushing, not stopping, simply continuing on its course. Our galaxy is like that leaf, carried by gravitational currents through the vast basin of Laniakea, influenced by structures like the Great Attractor and the Shapley concentration, all of it part of a larger flow that extends across the universe. And here on Earth, on this small world, life goes on. People sleep and wake. Seasons change. Oceans rise and fall with the tides, and the quiet turning of the planet continues, night after night. If you were to step outside under a clear sky, you might see the stars shining softly, the Milky Way stretching faintly across the darkness. Nothing in that view would suggest the immense motions and structures we have been talking about. The sky would look calm, almost timeless, and in a way that calmness is real. The universe is not only vast but also gentle in its rhythms, moving at a pace that allows quiet moments, still nights, and the simple experience of looking up and wondering. So as we return fully to the present moment, it may help to let those immense scales fade into the background, like a distant horizon barely visible in the evening light. The galaxies continue their slow drift. Gravity continues its patient work, and the universe continues to expand. But here and now, there is only this moment, this breath, this quiet awareness. The vast flow of the cosmos carries everything forward, but it does so softly, without hurry, leaving space for rest, for reflection, and for sleep.